Okay, everybody behave. You're now being recorded forever. Everything that you say now will be, set in stone forevermore or not. We'll see. In any case, so we're starting ray tracing in a weekend. I have never done any ray tracing stuff. I don't know how it will go. I saw briefly that the code samples are in C++, so I'm gonna I will have to translate them to Zig, and we'll see also how that goes. I'm not a C++ programmer. Also, I have a vague idea of what some of the constructs look like. Some stuff I will have to learn on the fly. Maybe chat will help me decode, some of the most intense C++ isms. And this is the second time I'm attempting to do something like this. The first time was OS in 1,000 lines of code, which you can find both on YouTube and on GitHub. On GitHub, you will find the source code. There's links to the VODs in the README. I don't know if the VODs link to the repo. They should. In any case, I'm Christoph-IT on GitHub, so you can find all the stuff there. The repository for the OS in 1,000 lines is called ChrisOS. This one is called ChrisRTX. It's a silly name, but apparently that's just how we're running with this stuff. Okay, so let's get started. Overview. I've taught many graphic classes over the years. That's not me, by the way. That's the book author. Often I do them in ray tracing because you are forced to write all the code, but you can still get cool images with no API. I decided to adapt my course notes into a how-to to get you to a cool program as quickly as possible. It will not be a fully featured ray tracer, but it does have the indirect lighting, which has made ray tracing a staple in movies. Follow these steps, and the architecture of the ray tracer you produce would be good for extending to a more extensive ray tracer if you get excited and want to pursue that. I guess that's basically what you do with the follow-up books, Ray Tracing the Next Week and Ray Tracing, a lifetime dedicated to ray tracing. That's the third book. When somebody says ray tracing, it could mean many things. What I'm going to describe is technically a path tracer and a fairly general one. While the code will be pretty simple, let the computer do the work, I think you will be happy with the images that you can make. I'll take you through a ray tracer in the order I do it, along with some debugging tips. By the end, you will have a ray tracer that produces some great images. You should be able to do this in a weekend. If you take longer, don't worry about it. I use C++ as the driving language, but you don't need to. However, I suggest you do. I won't, because it's fast. It's not. Portable. It's not. In most production movie and video games, renderers are written in C++. Unfortunately true. Note that I avoid most modern features of C++, good choice, but inheritance, bad choice, and operator overloading, bad choice, are too useful for ray tracers to pass on. God damn it. Okay. I do not provide the code online, but the code is real, and I show all of it except for a few straightforward operators in the Vectory class. I'm a big believer in typing in code to learn it, but when code is available, I use it, so I only practice what I preach when the code is not available, so don't ask. I have left that last part in because it's funny that what a 180 I have done. Several readers ended up with subtle errors that were helped when we compared code. So please do type in the code, but you can find the finished source code for each book. Okay, so they have it on GitHub. Okay, we're not gonna look at that stuff. And also the implemented code for this book, our philosophy for the included code prioritizes the following goals. The code should implement the concepts covered in the books. We use C++, but as simple as possible. Our programming style is very C-like, good, but we take advantage of modern features where it makes the code easier to use or understand. Our coding style continues the style established from the original books as much as possible for continuity. Line length is kept at 96 characters per line. To keep lines consistent between the code base and code listings in the books. Okay. To be fair, doing this without operator overloading is painful, a lot of vector math. Well, we'll see how it turns out when I do it. I mean, I get the idea in general, but I don't know. We'll see. The code thus provides a baseline implementation with tons of improvements left to the reader to enjoy. There are endless ways one can optimize and modernize the code. We prioritize the simple solution. We assume a little bit of familiarity with vectors. Yeah. If you don't know that, do a little review. If you need a review or learn it for the first time, check out the online graphics codex. You know what? Keep it open in a tab. Never hurts. Fundamentals of computer graphics, blah, blah, blah. Okay, project readme for information about this project. Okay, I think we can continue. I'll put an image. So that's our starting point. By the way, there is also another thing that I saw recently about ray tracers. So you know what? This is just one small one small aside, and then we can go back to the book. Has anybody seen recently? There was a video on YouTube that I saw about somebody making a game engine where they use ray tracing with audio, with sound. Does anybody remember? So, let's see. Ray tracing audio. I don't know if it was this. Ray trace sound on the GPU. I think this might be it. Let's see. No, the one that I saw was an explanation. So I guess it's the same idea. But there was a video that basically explained how all this stuff is achieved. And it might be the first one, actually. Maybe YouTube did give us a good suggestion.
Where you couldn't tell which direction a sound will be deeper than usual.
Yeah, where basically they use...
They also move in 3 dimensions.
They use ray tracing, and they use that to understand how audio should sound, how everything should sound. It's really cool. I guess my point is, apparently the title is A First Look at Ray Trace Audio. So I guess the point is that ray tracing is an interesting idea that obviously makes sense with light, but that you can apply to other things that aren't just light. I guess anything that is some kind of wave that propagates is a potential candidate for being modeled this way. Apparently doing it with sound also yields its own benefits. Okay, so let's start with the work. I'm gonna do Zig init. Oh, we don't have -m, unfortunately. This would have been a good candidate for Zig init -m. So we get a good Zig init. It makes a distinction between main and root. We don't care about root, so I'm going to remove source/root.zig. I'm going to go into the build script, and the build script this is the version that has a ton of comments and teaches you about everything about the build system. We're not learning about the build system right now. If you want to learn about the build system, I have a video where I explain how to do that. So we're gonna select every comment, delete it, and then let's see. We have module, we have the executable. Sure. Wait a second though. I think I might have deleted more stuff that I wanted to delete. Wait a second. Yeah, I deleted also the root source file. How did that happen? Let me see. S, and then we do... Oh, wait a second. Was I just looking at the wrong thing? So why is this? Okay, so I don't know. I did something wrong earlier. Okay, so this is based in root. We don't care, so we don't do this. We don't do the import. We just have main.zig. Who knows? Maybe we decide that then we'll need this in the future, but for now we don't. So take this out, take this out, take this out. That's it. Let's see. Do Zig SMD vectors support addition, etc.? Yes, they do, but they don't. But they don't support like vector style operations. So everything is a dot operation, I believe. And there is no matrix type. So there's also that. So long story short, if you're doing graphics or like anything where you need vector matrix operations, you need to implement them yourself, or you can use a library that implements them. There's Zigmath somewhere. You know what? Maybe we could consider also using a dependency to get this stuff implemented for us for vectors. We'll see though. Maybe the book guides you towards some of that stuff, and so we can just do it ourselves. Okay, so let's see. I have the build script. I have my main function. The main function has some stuff in it that we don't really care about. So let's remove this stuff. Let's see if it works, or if I left a build error somewhere. It runs. Okay, so we have our main function. Okay, next, let's continue here. Whenever you start a renderer, you need a way to see an image. The most straightforward way is to write to a file. The catch is there are so many formats. Yep. So what's the format that we're using? PMM. Plain text PMM file. Let's see. An example of a color RGB image stored in PMM format. There is a new line character at the end of each line. So, it's literally ASCII numbers, zeros. I'm guessing the alignment is just there for convenience and doesn't have a meaning in the format. PPM. Yeah, PPM. PPM. What? Let's make some C++ code to output such a thing. So main function, image width, image height, loop, and then what are we doing? We are double I divided by image width -1. This is also auto. So I'm guessing also, wait, what? And then this is all multiplied by 255.999. Okay, so we're basically taking the index, we're dividing it by the width. We are normalizing everything over 0 to 255 or 266. Like in any case, we're normalizing it over this range, which I guess makes sense. I guess this is int, so we're truncating. And then we are printing IR space IG space IB RGB. Okay, so like, yeah, integer. Okay, let's implement the same stuff. Const width wait, what was it? 256. Okay, 256. Same with height. Then we need to loop from 0 to them. So for 0 dot dot. What do we do on the outer, width or height? Oh, it wants height. Oh, it always puts height first. Okay, height for 0 dot dot width. Then we are, so they're using INJ. Why would you use INJ when you have width and height? Why would you want to use H and W anyway? So it takes I, divides it by, it takes W and divides it. No, wait, it takes, oh yeah, no, it's the inner one. Okay, so it takes W, divides it by width -1, and that is supposed to be a float. But X and Y is what you would use. I mean, in this case, H and Y seems, H and W seems good. So, sorry, wait, we're doing this for, we're doing this for red and green, and blue is just hard-coded to 0. Okay. So const, let's see, red equals, we said H divided by height -1. And this, we also want to then we want this to be a float operation. And then we want to multiply it by 255.99 and then truncate to int. So let's do this. This is going to be, I don't know, usize then we need to do this. And so we need to do float from int. I don't know if this subtraction will yield us a float operation, a float number. I think it should, because this one is an untyped constant. We'll see though, I'm not sure. So we have the float operation, then we want to do 255.99 times this, right? And then we want to int cast everything. Should be U8. That's fair. U8. And we want to int cast, and we want to, I guess we want to floor it. So, is it just floor? Yeah, floor value. Returns the largest integral value not greater than the given floating point number. Okay. Just multiply int by 255 and divide by height, and that's it. I think you're right. If we do that first, it should be the same, right? Yeah, let's, you know what? I'm gonna follow the book more precisely. Let's see what this shows. And then we can, float from int must have a known result type. Oh, fuck. That is annoying. You know what? That alone might be a good reason to do what you're suggesting right away. Yeah, this is kind of backwards, isn't it? Yeah, you can use add as, but generally speaking, I personally don't like using add as. Like if I add to, I would do this. FH, like float H, and I would do this. And then I would plug FH here. That's how I would do it. Let's start with this, and then let's do what Andrew is suggesting. There's no F32 from int. No, it doesn't work that way, because the way it works is that float from int understands what the target is from the result information. So originally, float from int took a type as the first argument. So you could do F32, and then you would pass the value that you wanted to cast to F32. The problem was that this syntax has a it has a foot gun attached to it, where you could do something like you at some point, this maybe used to be float 32s, and then you want to change this to float 64, and you forget to change a float 32. You know, maybe the expression is more complicated, and you forget it in the middle. You're casting something to float 32, and then these two things go out of sync, and you don't realize that. So you did want to upgrade to F64 because you wanted the extra precision, but now some of your math doesn't have that precision because it's still stuck to F32. And casting an F32 to an F64, like in, coercion, succeeds, because every F32 can be represented as a F64. So this is the problem. The problem is that if these operators allow you to write down what the target type is, then you could have surprising, like coercion could hide some bugs. While with this system, there is no way for these two things to go out of sync because they have the same source of truth. It's annoying. It's annoying as fuck. I get it. But this problem is real, and this mechanism solves it. Okay, so RG RGB. Next. Oh, these are the I versions. Okay, and then we just print them with a new line. So we need an output file. Oh, wait, it doesn't even print an output file. They just print a standard out and then do redirection, don't they? CMake? No, dude. What are you talking about? The fuck is this? No. Okay, in any case, you then redirect to a file. Okay, that sounds good. So we need access to std out. And we want to buffer because otherwise this thing is going to be slow. I don't know, maybe going forward if we do bigger resolutions. You still need in from float. I mean, that's what floor does, doesn't it? Doesn't it go to int? I think there's a floor to int that goes that truncates. Maybe this is not it, but I believe there is a built-in that does that. Same type as given. Okay. So not documentation. So let's see what we can use. Int cast, int from bool, int from error, from float. Let's see. Converts an integer part of floating point number to the result type. If the integer part of floating point number cannot fit in the destination type, safety check illegal behavior. Okay, so maybe we can just do this instead of floor. Let's look at seal. Oh, there we go. There's also trunk. Let's see trunk. Rounds the given floating number, point to an integer towards 0. Uses a dedicated hardware instruction when available. Let's trunk. Oops. Okay, so we need to print the standard out. Look at trunk signature. God damn it. Oh shit. Okay, never mind. Even round? But you know what? Let's leave it there. Let's see. I want to see the compile error, and then I'll fix it like you guys suggest. Why is it using 255.999 and not 255.0? Is it some weird precision thing? I don't. Probably. I'm guessing there's a reason why they do this. People in chat maybe can answer this while I fix this code. Actually, no. It's fs.file. Cd out. No definition found? Are you kidding me? Oh, wait. FS. What am I doing? Okay, we get std out. That gives us a file, and then we need to have a writer. Can we do std out.writer? Yeah. The interface, right? Yep. Okay. Is this new IO? Yes, not all of it. This more precisely, this is new reader writer. The new reader writer interface. Last of IO is not yet in master branch. It's coming though. It's coming soon. So out.print, and you want to print where said one thing, and yeah, digit space digit space digit, and we could even do the alignment. I don't remember how the alignment works. It's, I believe, what is it? Space greater 3, something like this. Like you say the character you want to put there, you want the alignment, the side in which you want the alignment, and then the number of seats. You know what? We can try this out and see how it works. And honestly, also, maybe we don't care about how nice the file looks like, but RGB. There we go. Zig build. Prominent compiler errors. Watch. Let's keep a watch open. Yeah, expected type 8 found F32. Okay. Confirmed. This is a problem. So in from float. Next problem. Expected type IO writer found const writer. Oh yeah. Error union is ignored. Yes. Okay, so we built. PPM was right. Do we have a PPM viewer? Cannot be opened. It may be damaged. Oh no. I don't know if we have a viewer at all on macOS. Later, it would be better to run optimized builds for speed. In that case, you would, yeah, sure. Oh, there we go. Toy viewer on my Mac. You're missing the PPM header. Am I? Oh, you're right. That's what was printed here, wasn't it? You're totally right. That's definitely what's missing. Good point. So what is this? This is try out.print p3 new line image width space image height. Oh, wait a second. Wait a second. Is this being printed in binary? No, because this is printing. This turns numbers into text. Okay, thank you, C++. Okay, so it seemed weird, but I just wanted to make sure. So new line, and then 255. I guess that's the range. And then new line. Okay. What did we mess up? Main function expected two arguments, found one. Right, where right, that's a bit of a problem, huh? Height, width. Is this what we expected to see? I think not. I think we might have done something wrong. By the way, I also have these this thing here, which might or might not do good things. So let's see what's happening here. Yeah, it's there's a double zero. Wait a second. No, that's like this. No, not open. I'm gonna stop messing with oh no, reloading killed my editor. Hello? Oh god. Missing new line in the loop print? Am I? Oh, I think you're right. Yeah, that's a problem, huh? Why is my editor dead? Helix, come on, man. Why are you like this? That's crazy. This is also gonna kill my today AMD. Wait, what? It's still here. Oh no. Well, you know what? Let's imagine that this never happened. Let's start again from scratch with the editor, I mean. So maybe I was right then with this the first time. I think the new line is wrong, right? We don't want a new line. We want the new line only. Wait, new line always? Wait a second. This does not sound right. This is doing a new line every time it prints 3 numbers. While here, this is doing, well, not this. Flash. Good point. We also need to flash, yes. But you know, this screenshot here seems to suggest that Oh no, you know what? This is a 3x2 image. And it's not really, I guess new lines are not important. 3 columns and 2 rows. Maybe they are. Maybe any space works. Yeah, maybe any space works. Yeah. Oh, all white space is equivalent in PPM. Yeah, there we go. That makes sense. Let's do this. Let's see if I'm getting the alignment correctly. In any case, okay. Still black though. So the numbers are indeed changing. At least some of them. No, actually they are all changing. So this is correct in terms of, well, numbers moving around. Also, look, this is doing indentation correctly. It's adding 2 extra spaces to keep everything aligned. So this is good. Although it does not seem to be doing it for, wait, I need to cut it again, I guess. Yeah, okay, now it's doing the extra spaces also for this guy. Wait a second, why does it end like this? Did you specify the color range? I think I did. It's just 255, right? I'm curious though. Oh, right. We need to flush, by the way. So yeah, the problem here is that we're not flushing. So to do, as we're here, out.flush. Also, suggestion for people who program in Zig, you do not do this. I know that it's tempting to say, well, okay, here I have my writer, and then I'm going to defer flushing. But you can't, and you shouldn't. First of all, flushing can return an error because it's an IO operation that could fail. And then in defer, you can't try, because try is something that makes you return. But if you're running a defer statement, you're already returning, and you can't change what type of return you're doing. You can't change the return value. So then you say, well, then I take try out and I do catch, do nothing. That works, kinda. Like, sure, now it compiles. But generally speaking, you don't want to flush if you encountered an error before. The idea is flushing is you finalizing the write. And if you had errors earlier, it's kind of wrong for you to attempt to flush afterwards. Something already went wrong. You should leave that stream alone. Okay, there we go. We got it. We just needed to flush. Delightful. Okay. Let's see. Creating an image file. Yeah, we got this. We don't even need Toy Viewer. It works on macOS itself. Let's see. Hooray, this is graphics hello world. If your image doesn't look like that, the output file text or blah, blah, blah should look like this. Yeah. We don't have everything nicely aligned. Can I open it in this editor? Will it poop itself? No. Okay. Yeah, look at this. This is nice. Yeah. Yeah, this is nice. Okay. Next, to do adding a progress indicator. Before we continue, let's add a progress indicator to our output. This is a handy way to track the progress of a long render and also possibly identify a run that's stalled due to an infinite loop or other problem. That's fair. Our program outputs the image to standard output. So leave that alone and instead write to the logging output stream. Okay, so here's how we're gonna do it. We have a nice thing called const progress equals std.progress. Actually, it's uppercase, isn't it? Yeah, it's uppercase. So progress, and we can use progress to, well, as the name implies, signal progress. So let's do this. How do you use it? I don't remember how you use it. Start. Initializes a global progress instance, asserts that there is only one progress instance, call node.end when done. Okay, what are our options? We need to pass in a draw buffer. Must be at least 200 bytes. Okay, so we're gonna pass in a buffer, and I think the rest of the options are kind of fine. Oh, there's also a root name that we can put here, and there's also an estimated total items, which seems good. So let's see. So up here we do uh, PR equal PR equals progress dot start, and we're gonna need to pass some options var pbuff progress buff 2024 u8s. What's the name of the option? I forget already. Draw buffer and then root name are the ones that we care about. Draw buffer equals pbuff. Well, for now I think this is fine, and then we defer pr dot end. Yeah, finished a sort of node, thread safe. Okay, and then we have the estimate, right? Estimated total items. Estimated total items is, I guess if we move this up here, you know what? Maybe we can even take them out and use them as global constants. And we can say that this is going to be height times width. And then I think it was a root name. Raytracing, I guess. I don't know. It's not stdr, it's stdlog. Yeah, fd3. Man. Okay. So we have this. The problem is that we're not starting like a new progress every time we enter here, which, by the way, it's probably a non-insignificant amount of overhead. So this is probably going to make more sense once we have a less tight loop. So for now, I'm just going to leave it here. You don't even see it. Like, you don't even get to see it. It's just too fast. So let's worry about this later. And in any case, they also print what? Yeah, look, they also print this also in the only in the outer loop. So they make progress in the outer loop. We're going to tweak this as we proceed. It's fine. Vec3 class. Almost all graphics programs have some classes for storing geometric vectors and colors. In many systems, these vectors are 4D, 3D position plus a homogeneous coordinate for geometry, or RGB plus alpha transparency. For our purposes, the 3 coordinates suffice. We'll use the same class vec3 for colors, locations, directions, offsets, whatever. Some people don't like this because it doesn't prevent you from doing something silly like subtracting a position from a color. They have a good point, but we're going to always take the last code route when not obviously wrong. In spite of this, we do declare 2 aliases for vec3, point3 and color. Since these 2 types are just aliases for vec3, you won't get warnings if you pass a color to a function expecting a point3. And nothing is stopping you from adding a point3 to a color, but it makes the code a little bit easier to read and to understand. Okay, so let's see. Well, now, oh man, now it's time for these operations, huh? Yeah, that sounds good. That sounds great, actually. Let's do it. I'm tempted to make a new file for this. Maybe you can call it math.zig or vec3. This is how to write PPM faster. Yeah, so right, this is your solution where you do the multiply first. That makes sense. Yeah, P6. Oh, it's binary instead of ASCII. Oh, that is interesting. I did miss out that nuance. Yeah, you're right, because you're not writing ASCII. That seems a nice improvement. I guess the problem is that it doesn't allow you to inspect visually what's going on with the file format, huh? But at the same time, if you don't do terrible mistakes, this thing seems easier. I'll keep this in mind. Thank you. I'm going to open this, keep it around. And if at some point we need to upgrade, we're going to upgrade. Okay, let's do, so vec3 or math? Let's do math.z for now. Okay, class vec3. You know what? Can I rename this file? Yeah, you know what? I'm going to write it also as source.vec3.zig. And then I'm going to delete math later on so that we can use a top class struct at this point. So here's the idea. Vec3 has an array of 3 doubles. Is that how they do it? Or you can do move. Oh, thank you. I didn't know. I searched for rename and nothing showed up, so I stopped there. I use a vector for my RT. So you did it like this, right? So you did so it's a struct, and then we put in here call it E. What do we call it? Let's call it V, I guess, in our case. And so you say V is at vector. I guess it's uppercase. Yeah, 3 element F32. Wait, doubles are F32s or F64s? I don't remember. Okay, by the way, I never used, it's 64. Okay, though, so 64 it is. Let's go. Wouldn't want to. You're right, float is 32, double is 64. Okay, so we have V vector, and then we need to implement all the things. So there's a couple of constructors here. Do I care about constructors? No, I think these guys suck, so I don't care. Getters for XYZ, I think that's fair. Oh, but I can't call if V is the field. God damn it. I see. If V is the field, then I can't do vector. So okay, const vector equals at this. Vector returns a F64, and then we can say return X. Return V dot E at 0. Z 2 1 Y. Here we go. Declaration not allowed within container fields. Yeah, something south is being parsed as something else. Okay, we don't worry about this. So operator subtraction. Right. So I think this subtraction is doable with just normal. Oh no, wait, this is negation. This is not subtraction. I guess for us would be this. I think. Then we have indexing. We don't need to do this. Double ampersand indexing. Like a reference indexing. I don't know. I don't care. Equal assignment. I think we have this. We don't have to make it our own version. Negation works on vectors. Oh, never mind then. Fuck this. Um, this we have, I believe. I'm guessing this we have also. Oh no, wait a second. Operator divided equals takes these and multiplies it by 1/t. Do we have this? Wait, what was the other one that I removed? Oh, right. Do we have this? Can a vector be multiplied with a scalar? It won't work on start with vector inside. You're right. Are you saying that we shouldn't do this and we should just have a naked vector? So we use naked vectors and then we make functions that operate on naked vectors? That might be better, wouldn't it? You need to splat the scalar. Okay. So by the way, I never really worked with vectors, so that's why I'm not sure how to approach this, and I need to figure it out on my own. So, okay, let's do this. So let's say that we do this instead. We do this. Okay, so if we do it this way, I think this is not bad. And then we need to move this file then to source slash, I'm going to just call it vec then, or v, vec.zig. Let's see how it goes. Again, I'm not sure. I'm just testing stuff out. So yoink what Mason has. I know that I could yoink what people have already made, but we should be doing this work ourselves if we're doing everything from scratch, shouldn't we? But you know what? At least there's nothing bad in looking at what they do. Also, probably Mason has something more fancy than what we need. Two-dimensional vector. Wait a second. Two? What? And so he has some nice constants for this. Okay, he has splat, equal, scale. Yeah, this is all good stuff. Okay, you know what? We can come back to this later on if we find what we are doing to be absolutely inadequate or it's too much work. For now, I want to experiment a little bit with what we have, and I want to see if at vector is going to help me out. So the multiply assignment with a number. So I guess basically we want splat. Wait, do we add splat? Produces an array or vector where each element is the value scalar, the return type, and thus the length of the vector is inferred. Scalar must be an integer, bool, float, or pointer. Okay, so we should be able to do splat with the other stuff. Okay. Requires the result location. Okay. So for now, I'm not going to implement any of this stuff. I'm going to implement it as I need it, I guess. Length uses length squared. So this is like the vectors. What's the name? Oh man, what's the English term for the? I mean, they use length here, but I think there's a more appropriate term for this, right? The magnitude. Thank you. Yeah. Okay. Norm? No, I don't think it's norm. I think it's magnitude. What we're referring to. It's like the length of the arrow, right? And the length of the arrow is constructed by by doing this. It's like the Pythagorean theorem, basically. In any case, let's call it length so that, although we do like, you know what, fuck it, magnitude. Returns an F64 in its return std.math.sqrt. No definition found because we don't have std. By the way, we're really taxing ZLS because we have a bunch of C++ code pasted in our stuff in here right now. uh, Now, can we do this on a vector? Can we do square root of std dot, what is this? I don't think there is a, we don't have it in the standard library, something like this, right? So we have to compute it. SQSum. Magnitude V is a vec3. Let's see if SQRT supports this stuff. Mason's SQRT would work. God damn it. It doesn't work? No, wait, it should. Wait. This is just a normal number, right? This is just an F64. This works. 0.3, right? These are the other things. IO stream operator. So it's giving it a FMT. We can actually do this. Pub function FMT. W is a pointer to a writer. Why not add SQRT then? Can we? Do we have an SQRT? First, the square root of a floating point number uses a dedicated arrow instruction when available. There is reduce. Okay, so how would you implement this with reduce then? Can somebody share this with me? I'm gonna write the formatter in the meantime. So I think it's writer and then wait, no, it's V, a vec3, and then here's a writer. And I think that's actually it now. This is void two, and then it's w dot print, and it's printing what? Component space as digits. Okay. No new line though. No new line. And okay, and then we try this. Okay, so this is FMT. Okay. So this is okay. Then this is sum between two vectors. I think we have this, so we should be good. Multiplication doesn't seem interesting. This is multiplication with a scalar. Maybe we'll need to implement it. I guess we'll see. Division with a scalar. There we go. Now this is the interesting stuff. Dot products, cross product, and the unit vector. Yeah. Mine is so wrong. Let's see. What did you write? Reduce add reduce add v times v. Yeah, you multiply everything and then you add all components. Yeah. So this would be return sqrt of reduce dot add v my star v star v. Nice. Okay, let's do dots. Function dot Turns on F64. um, so we are returning. Okay, so this can be the same thing, right? So return, well, similar thing, reduce dot add LHS times RHS. You forgot args in your print. Oh, you're right. Okay, so here we do this. So this should be our dot. Then we have cross. Cross, I believe can you do this with reduce? You can't really, can you? Why is it not format? Because format doesn't exist, or does it? Well, because it's not format because I'm not, vec3 is not a struct anymore. So I'm not adding a format method to struct. I'm basically, I don't remember exactly how we glue everything together, but I believe that you need to. Yeah, that also doesn't exist anymore. I think it's now called stdfmt alt. So I think you basically do this. And this returns a struct. Yeah, there we go. A struct that has the format method. So this is how you do it. Pub const fmt equals alt of, let's call it format then, of vec3, comma, format. There you go. So FMT is what now we can use to do formatting. Mm-hmm. I guess we'll see later how this plays out in practice. Okay, so cross multiply, right? Yeah, I think this just has to be written out manually. So LHS, same signature, well, almost same signature. So LHS at 1 times RHS at 2 minus LHS at 2 times RHS at 1. Then 2, 0, 0, 2, 0, 1, 1, 0. And then unit vector. Which unit vector, is it also called in other ways, like normal? Is it like norm this thing? No. I mean, I get it. Unit vector is the same vector, but with magnitude 1. That I get. I wonder just if it has other names. It is a form of normalization, right? So, but is this the norm? I'm not sure if this is the norm. Also, you know what? Another thing that is causing confusion here is I'm used to Italian terminology of this stuff, which I'm also forgetting. And then mostly it's the same when it comes to norm is magnitude. Oh, I see. It mostly translates to English, but not always. Normalize means dividing by the norm. So norm is the magnitude. Okay. Okay. Okay, let's just call it unit then. So unit of v vec3, and I think we can. So can we do this with reduce? No, because we're not reducing anything. We need to splat, right? So we need to take v and divide it by at splat. And then we need the scalar that we want to splat. And the scalar is the length. So we can do magnitude of v. Can we do v dot magnitude? We can't, right? Would be nice though. Maybe this is an interesting solution. Nah. Magnitude of v. Okay, and you guys were saying that this is not gonna work because it needs things. Let's see. Duplicate start member name dot. Wait, didn't I write cross here? What happened? Let's see. Undeclared type writer. Splat must have a known result type. Fine. Honestly, this doesn't seem too bad. Okay. Christoph, call it dir as in direction. You're going to have a divide by 0 with that implementation. Well, that's how they implement it, though. How do you implement it in a way that a vector of magnitude 0 can make sense? Also, wait, a vector of magnitude 0 requires all members to be zeros, right? Call it dir for direction. I think I prefer unit, special case it. Okay. So like if the vector is 0, I return 0 and I don't do the division. I mean, that makes sense. Right, so we can do this, right? If mag equals 0, return 0. It's not going to work, is it? Well, I guess we need to use this. But also we can do better, I think. We can say 0 and return 0. And we have constants, right? So we make them. So we do popconst 0 equals there we go. Okay. 0 is signed. Mag should always be positive. I'm not sure what you guys are talking about. I guess I'm gonna learn this stuff as I proceed. Yeah, okay, let's continue and then let's start using this code and see, and just watch it poop itself once the time comes, I guess. So using our new vec3 class, we create a new color.h header file and define a utility function that writes a single pixel's color out to standard output stream. Write color. So, okay, so the function from before takes a vector and interprets it as a color and then also prints it. Okay, so that's our previous main. And they put it inside color. Minus 0 is not positive 0, so x equals 0 might be false for magnitude being 0. But magnitude is always a positive value. Where is it? Oh, but you're saying, oh no, magnitude is always going to be positive. I'm just plotting it. Also, wait, why am I doing this? I can just test magnitude. I don't need to splat it first, right? Okay, let's do it like this. Const mag equals this. Magnitude of V. And then here we do, if magnitude is 0, we return 0. And down here we do, let's call it mag3. And then we do mag3. And mag3 is splat of mag. Float 0 is signed. Okay, but is magnitude ever going to be negative? I don't think that magnitude is ever going to be negative. If any component is negative, it becomes positive from the multiplication, and then you sum numbers, so it can't be negative. So I don't see the -0 problem being a problem in this case. Also, more specifically, we also don't need to compare splats. After splat, we can compare the original value. So you're saying the problem is, okay, you know what? I don't know what the problem is. It's fine. I'm gonna go with me. If it's not greater than 0, okay. But is it really ever gonna be negative? How can it be negative? So we were saying that this loop is what we're turning into a dedicated function. Print color, they called it. Print color, and you pass in, I don't know what. We're gonna figure out what you pass down here. Let's see. Oh, write color, they call it. Okay, write color takes in a vec3 and prints it. Okay. To be honest, this could be an FMT thing for us, now that I think about it. This is basically a color format. You know what? Let's do it this way. Yeah, let's do it this way. FMT, and then we do color FMT. And actually, this function should not be public. Do. Okay, let's see if we can do it in a smarter way. What was the idea? The idea was you take the component, you multiply it by 255 first, and then you divide it by height and width second. Also, wait a second, because here we have some values that are, no, wait a second. Oh, right, because we're not coming up with a specific color, we're just printing what colors are already there. So this is taking the values, the components, multiplying them by 255.999, and then printing them out. So what we have here is not really useful. It's a try w.print. DDD. Right. I think this should be it. So this is color format. Okay. Int cast won't cast floats. What do you mean? We were doing it here. Oh, sorry, it's in from float. You're right. Yeah. Okay. Okay, next. We can now change our main to use both of these. So the main function now uses the color printing and uses a bunch of overloaded operators now. Okay, let's see. Okay, let's see us make this happen. So it works by doing pixel color. Pixel color is going to be a vector. And it's a color constructor. So now the C++ metaprogramming stuff is not, it's about to make me go insane. So we're constructing a vec3. This is an initializer. And we have the integer turn into double divided by width minus 1. The other one, and the third component is 0. We make a vec3, and then we try to print it. And that's how we continue doing it. By the way, we also lost all new lines in the process because write color does not do a new line at the end. No, never mind. Print color does have a new line at the end. Okay, sure. Let's add a new line. Okay, so here we do so we were saying the first component is outer counter, so height, width, yeah, the inner one, sorry, width divided by image width minus 1. So this is H, and this is actually 0. Also, this is not really print color. This is just the main loop. We don't have vec3. We can add it. We can have it. It's ours. Const vec3. Let's do vec equals at import vec.zig. Const vec3 equals vec.vec3. Right, and these are called width and height for us. And then we do std, try out.print f. And then we need to do vec.color. And color wants color pixel. This is a pixel. Okay, so this should roughly be it. Let's see what Zig build has to say. Incompatible types use size and comp time float. Right. So what if I take this out? Will you be happy? I don't think you will be happy because we need to float stuff, right? Except I F64 found U size, right? How do we float this stuff? We need, right, we were making them, if we undo a bunch, we previously were making them explicitly floats. I'm gonna yank this, redo everything, and here we can paste this stuff. That's how we were doing it. So it's W divided by F W, H divided by FH. And maybe we're not done, but that needed to happen. So let's see, incompatible types, U size and F32. Right. Flow from int and inverse works on vectors. Yeah, but we have the operation around it, so it's not gonna work, I think. We need to, like, if I float from int this is still not okay, right? Because we need that division to be float division. So this is not gonna solve it. Invalid built-in function float from int. This is not going to solve it. Let's see. Oh well, that's This should not solve it, I believe. Yeah, because the problem is the inner operation. So we can do this, but since it's in an operation, we don't have a known result type. So this is not going to work either. So we need a floated version of this value before we do the division. There's no real solution, is there? And actually, now that I think about it, do they both need to be floated? Yeah. Just create to F32 function. And it's a good point. That would solve it, wouldn't it? We make our own casting function. You know what, though? I would like to continue with this path a little bit more. Let's see what happens. Oh, also... wait a second. We were doing FH divided by height minus 1.0. So that's how we were making it work earlier. That's what was solving it. So I actually got it wrong. This was like this. This was FW divided by width minus 1.0. And this was working. Let's see. Int from float must have a known result type. Okay, so we're back to... Okay, now we're seeing errors in our back implementation. Also, I'm surprised that ZLS is not helping us. What's going on with ZLS right now? I would expect to see... ZLS to give me errors in here. I'm gonna restart my editor just to understand what's going on. Why is ZLS not working? Oh, there we go. Zig accept path, expected actual path but got zig. That's fine though. That should be fine. Okay, so the error here is int from float must have a non-result type. And it doesn't. Why does it not do that? Oh, wait. It makes sense that it doesn't do that because we're not making a vector like or anything like that. We're making three numbers. Int from float. So how do we make this nice? I'm not going to use as. I don't like as. You can do it like this. Replace dot for vec3? No, that doesn't work because we're doing something else. If that was the case, it would work. Uh, oops. I'm using underscores because I have functions that have the same name. Error type is not a function. You're right. How does this work? We need to. This gives me a type, and it has a format. We make an instance of this guy, right? This should be like this, basically. So in main, we need to use color like this, I guess. So vector dot color equals pixel. Sorry. Does that work? Yeah. Okay. Success. It works. Okay. We have successfully added extra functionality. Let's see. The Ray class. Rays a simple camera and background. One thing that all ray tracers have is a ray class and a computation of what color is seen along a ray. Let's think of a ray as a function, p, parameterized by t, that does a plus t times b, where p is a 3D position. What do you mean p is a 3D position? It's a fucking... Wait, what's going on? It's a 3D position along the line 3D. A is the ray origin and B is the ray direction. The ray parameter T is a real number, double in the code. Plug in a different T and P moves the point along the ray. Yeah, so I get it. What a way to explain it, though. Add in negative T values and you can go anywhere on the 3D line. For positive T, you can only get the parts in front of A. And this is what often called a half line of array. Okay. Yeah, it's linear interpolation. That sounds good. We can represent the idea of array as a class and represent the function p as a function that will call ray at t. Class array. Okay. Let's make a array file. Uppercase ray? Should it be uppercase ray? What does it contain? Private. Point 3 origin, back 3 direction. Yeah. Point 3 origin, back 3 direction. Interesting. Okay. So point, back 3, direction, back 3. Const ray equals at this. Const std import std. Actually, I don't know if we need std. We do need back 3 though, that's for sure. Okay. what does it have? Origin, direction. Okay. We don't care about this shit. At for linear interpolation. Okay. So at ray, copy. Well, you know what? Easier. I don't have to think. So returns a vec3. And in here we do return. Oh, this was origin, yeah. Ori. Origin, direction. Okay. So return origin plus t, which is a parameter that we don't have. F64. So this is t times dir. Okay. So origin plus t times dir. So what could we call t times dir then? Blind forest gene. What? Oh, it's a joke. Oh, okay, I get it. Offset. Scale. Let's go with scale. Okay. I'm not sure, but for now, it's fine. Displays. So scale, we're saying it's well, let's do tv3. T3 equals vec3 equals at splat t. That's splat multiplication, right? That we do not implement. Yeah. So wait, what's the name? It's dot multiplication with a scalar. So origin plus t3. T3. Okay, so this should be it. And T3 is splat T. Did we do it? Wait, something is missing. Origin plus T3 times R dot direction. Okay, there we go. This is it. Okay. For those unfamiliar with C++ functions, origin and direction both return an immutable reference to their members. Yeah. Sending Rains into the scene. Now we are ready to turn the corner and make a ray tracer. At its core, a ray tracer sends rays through pixels and computes the color seen in the direction of those rays. The involved steps are calculate the ray from the eye through the pixel. Scale is multiplying a vec by a scalar. Yeah, that's true. Maybe it's helpful to have. We'll see if we are going to need it. Yeah, that's a good point. If we're going to need it, we'll see. Determine which objects the ray intersects and compute a color for the closest intersection point. Okay. When first developing a ray tracer, I always do a simple camera for getting the code up and running. I often got into trouble using square images for debugging because I transpose X and Y too often. So we'll use a non-square image. A square image has a 1-to-1 aspect ratio because its width is the same as the height. Since we want a non-square image, we're going to do 16 by 9. Sounds good. I think this is 16 by 10. Actually, no, this is 16 by 9 right now because I'm using a non-Mac screen. Like Mac laptops are 16 by 10, but this is a Mac Mini. For a practical example, an image 800 pixels wide and 400 pixels wide has a 2-to-1 aspect ratio. The image aspect ratio can be determined from the ratio of its width and height. Yes, however, since we have a given aspect ratio in mind, it's easier to set the image width and the aspect ratio, and then using that to calculate its height. This way, we can scale up or down the image by changing the image width, and it won't throw off the aspect ratio. Yes. We do have to make sure that when we solve the image, the resulting height is at least 1. In addition to setting up the pixel dimensions for the rendered image, we also need to set up a virtual viewport through which to pass our scene rays. The viewport is a virtual rectangle in the 3D world that contains the grid of image pixel locations. If pixels are placed the same distance horizontally as they are vertically, the viewport that bounds them will have the same aspect ratio as the rendered image. The distance between two adjacent pixels is called pixel spacing, and square pixels is the standard. To start things off, we'll choose an arbitrary viewpoint height of 2.0 and scale the viewport width to give us the desired aspect ratio. Here's a snippet of what this code will look like. Do we need to implement this? I think we should. We don't know yet where we want to put this stuff, but I think we're gonna do 235 one for cinematic effect. Maybe I should. You know, we were doing 235 at Software You Can Love. Actually, it was even it was even steeper than 235. 235 is what I wrote here, but I think at the cinema when we were there for real, you can also see, right, that this box here for the live stream has this aspect ratio. I think it was even bigger than this. It was like 250, I think. Anyway, yeah, sorry, setting this stuff aside. So we don't know where to put this stuff yet, but I guess we can implement it and then we decide where to put it later on. So, oh, you know what? I'm going to do something unholy. I'm going to modify the original code. So const aspect ratio. Oh, I guess we can put this here then. Height is image width divided by aspect ratio. Oh, it's also set to 400. Okay. So, okay. So width 400. Height is going to be image width divided by aspect ratio. So int from float of width divided by aspect ratio. I think aspect ratio, well, whatever, we can leave it like this. And ensure it's at least 1. It should not be a problem. Like, why? When would the problem? When would this be a problem? You know what? Okay, so this is doing. Okay, let's make a block. Let's do some code in a block. So h is this if h is lower than 1, break VLK with 1, else break VLK with h. Oh, you know what? Let's continue with this. Const. Okay, so this works. Instead of 16 by 9, use 15 by 8, so the diagonal is 17. Wait, why? What would that do? I don't know what I would do. By the way, what? Add. Oh, we have mul add. I didn't know we have mul add. Okay, fuck it. Copy. Take it. I'll take it. By the way, if this is bugged, Andrew, it's on you. Everybody's gonna hate you. Just putting it out there. No, I'm joking. It's not gonna be that. Okay. I'm gonna leave this commented out just to double check what our intentions are. You know what? Pause and endure is not bad, is it? Although origin and pause. I'll keep origin for now. Okay. So viewport height times with double. So it's image width. I guess we can do 0.0. Oh, you know what's a trick? You do plus 0.0 divided by image height. And now I get why he called this image that. Oops. Oh my god, why am I doing this? There we go. Okay. If you're wondering why we don't just aspect ratio when computing viewport width, also wait, did somebody else say something else? Square root of 15 by 15 plus blah 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 17. Right, and we care about this when we're doing certain vector computations, right? Because we're square rooting certain vector computations. Is this important when it comes to our image size and aspect ratio? Well, in any case, if you're wondering why we don't just use aspect ratio when computing viewport width, yeah, it's because the value set to aspect ratio is the ideal ratio. It may not be the actual ratio between image width and image height. If image height was allowed to be a real value rather than just an integer, then it would be fine to use it. But the actual ratio between width and height can vary based on two parts of the code. First, image height is rounded down to the nearest integer. Yes, we're using pixels, which can increase the ratio. Second, we don't allow image height to be less than 1, which can also change with actual aspect ratio. Note that aspect ratio is an ideal ratio, which we approximate, because it's pixels. Okay, so next we'll define camera center, a point in 3D space from which all seen rays will originate. Oh, I see. So it's like it's our eyes that light things up right now. That's that's in a sense, it's almost a philosophical statement. When they say beauty is in the eye of the beholder, in any case, in the person that watches, in some ways, light is also in the eye, or actually not physically. That's not really the case, but you get the idea. How could mirrors be real if our eyes are not real? Yeah, there's also that. That's another piece of amazing wisdom. Yeah. Let's see. We'll define camera center. Also commonly referred to the eye point. The vector from camera center to the viewport center will be orthogonal to the viewport. Yes. We initially set the distance between the viewport and the camera center point to be 1 unit. This distance is often referred as the focal length. Oh, yes. For simplicity, we'll start with the camera center at 0, 0, 0. We'll also have the y-axis go up, the x-axis go right, and the negative z-axis pointing to the viewing direction. Yeah, this is like the finger rule. Right-handed coordinates. Wait, are those the normal ones? Wait, are these the normal ones or are these the Microsoft style weirdo ones? And by the way, I might be I might be using judging terminology that maybe I this is the left hand, right? So this is what you do normally, right? When you like study physics, this is normal because I remember that a while ago, Specs guy ran me through how to write shaders for what was it? DirectX, and they have everything backwards. They had everything absolutely backwards. Okay, let's see. Now the inevitable tricky part. While our 3D space has the conventions above, this conflicts with our image coordinates, where we want to have the 0th pixel in the top left and work our way down. Spread your legs 90 degrees and sit on floor. Yeah. I mean, yeah, left hand rule. That works. I mean, you guys are seeing it backwards, but this is my left hand. As we can scan our image, we'll start at the upper left pixel, scan left to right across each row, and then scan row by row, top to bottom. So we're doing yeah, we're deltaing to the right and we're deltaing to the bottom. Sounds good. Why is it U and V? God damn it, man. Anyway. Our pixel grid will be inside. Actually, you know what? Maybe it will make sense afterwards, but for now it doesn't seem particularly useful. In any case, we'll use vector from the left edge to the right edge and a vector from the upper edge to the lower edge. Pixel grid will be inset from the viewport edges by half the pixel to pixel distance. This way, our viewport area is evenly divided into width times height identical regions. Here's what our viewport and pixel grid will look like. Okay. In this figure, we have the viewport, the pixel grid for a 7:5 resolution image. Yeah, 1, 2, 3, 4, 5, 6, 7. Yep. The viewport upper left corner Q, pixel 0, 0 location. Yep. Viewport vector U, then V, viewport vector V, and the pixel data vectors delta U, delta V. And the length of this vector is the pixel to pixel distance, right? Okay, so this is the new code. Color, ray color. Huh? Ray color takes in a ray. Also, what the fuck is this syntax? Const ray %r. Fine. But also, it returns a hard-coded 0. Fine. I guess we're gonna change these afterwards. Yeah, I guess so. Takes a reference to ray. Unlike a pointer, can't be null. Ooh. So, image auto aspect ratio. So this is what we just did. Focal length is new. So let's do focal length. Also, look at how weak they are. Look at this. This math is in their main function. Disgraceful. We don't do it in the main function. We do it out here. We solve these at comp time. No way we do this at runtime. I mean, I guess ideally C++ code goes through the optimizer and everything happens at runtime. But by putting this stuff here, the language guarantees that all this computation happens at compile time every single time, even in a debug build with like 0 optimization passes. Just pointing that out. Okay, so we have focal length. Camera center 0, 0, 0. Oh, it's a shame that I can't do this. But we can do vector 0. Calculate the vectors across the horizontal and down vertical viewport edges. So viewport U, viewport V. By the way, this is also all stuff that can be done at compile time. I'm going to copy this and translate this. Okay, const. Viewport U is colon vec3 dot curly const pixel delta U. This is not going to work. We're going to need to translate this. Okay. Oh, wait. This is just a very long comment. Okay. So user identifier image width. Yeah, it's EMG width for us. EMG. But this is not going to work. Then camera center minus. I guess we can do this. Maybe. Minus viewport U divided. Oh, God. Okay, there's a bunch of math here that we're going to have to split off into multiple steps. They're spamming the Going Live Discourse channel. Thank you. Delete message, report. I sure want to delete this message. You can hold down shift when clicking delete message to bypass this confirmation entirely. No, but I want to ban the person first. How do you ban the account? Oh, there we go. Right click. Oh, you have to right click on the account name. Ban this account. Suspicious of spam. Delete all. Ban. Why did it not remove the message? Did it not remove the message? Okay. Okay. There we go. Okay, sorry all. Hey Snextron, are you using GPU for ray tracing? I don't have anything right now. I just have a bunch of C++ code that I'm slowly digesting. That's all I have for now. Thank you for the report, by the way. Thank you all. So this stuff should be fine. Except this one. We need to splat these guys. Oh, that's annoying. So we can do all this stuff in a block, I guess. Image W3. Vec3 equals at splat img with, and then we break VLK with viewport view divided by EMG W3. So there we go. And height has the same problem. So pixel delta V is image H3, height H3, viewport V. There we go. C++ code? Yeah, because I'm following ray tracing in a weekend, and it has C++ code samples. So that's just life. Okay, so this is a little bit complicated because they by the way, the fact that they keep mixing and matching different types and they are leveraging um, operator overload to have all operations mix up. I don't know. I find it weird. I guess it's a mindset. Once you get into the mindset, you can accept it and like I don't know, even love it. But how is this weird? It's C++ bullshit magic. Except I get it that in the math case it's less bullshit than in the uh, random. I don't know. Like, look at this. What the fuck is this? What is this? Why are you shifting left strings, man? Why are you shifting? Why are you shifting left a space? What even is the point of this? This is just silly. Just print, man. Stop shifting. Just print. Like, they're doing like Fast and Furious here. I don't know. Let's see. So camera center minus a vector minus viewport u. Is that a vector? That is indeed a vector. Actually, you know what? Let's set this in stone so that we don't ever get confused about this. That's a vec3. Oh wait, this is pixel delta in any case, but that's fine. So camera center minus another vector minus viewport u. We were saying it's a vector divided by 2. So let's see, viewport u divided by 2. Okay, so we need to make this vu of, I don't know, let's call it vu half. This need to be splatted though. That's annoying. I'm trying to think if we should have a splat at this point operation. I think we should have a splat operation. Using add splat every single time is kind of annoying. It's forcing us to make too many temporaries. Let's add splat. Wait, no, it's not exactly splat that we want, right? Because the problem is that's like division with, oh god, right? Because then you have the problem that are you doing this scalar multiplication? Are you doing scalar multiplication, division, or whatnot? So, but let me think about it for a moment. I can do splat, and doing splat allows me to splat in line without temporaries, right? Yeah, that's wrong. Okay. I get it. So we don't get a vec3, we just get any type. And then we return a vec3. And in here we can return at splat. And yeah, and that gives us a splat to what we want. So with this, we can do vec.splat. We don't need this, and then we don't need the block anymore. I guess could be better, could be worse. I'll take it. Yeah. Okay, so here we can do then viewport u divided by, we're going to put parentheses, but we can do viewport u divided by vec.splat 2. And that should work. Although I have to say this whole formula kind of sucks. I might want to do this regardless. Oops. There we go. Also, this is kind of ass. What is this guy supposed to be? It's a vector 3 that has focal length at the XYZ. Yeah, I mean, that makes sense. Okay, I'll leave it as this right now. In boost vector, I think you can write V and then you shift into it 1, 2, 3, 4 to pen values. Delightful. Delightful. You think with work Zig won't be able to infer it? Will it? We want it? Well, if it doesn't, then we're gonna make a dedicated variable for it as well. Okay. And then we have pixel lock. So viewport upper left. What's viewport upper left? I believe this is a vec3, right? So it's a vec3 plus vec.splat 0.5 multiplied by pixel delta u. So like this. Which is a vec3 multiplied by another vector. Sum to another vec3. So this is okay, I guess. We got this on a new line. Yes. Okay, so we should have all the math. We'll see what happens with this guy. Okay, so we have all this stuff. Then we do auto pixel center is pixel 00 location. Viewport upper left. The first pixel is the viewport upper left. Yes. Plus 0.5 multiplied by pixel delta u plus pixel delta v. Why are we doing this? So we're summing two vectors. And then we're dividing by... We are basically dividing them by 2. Why are we summing and then divided by 2? Is that like a poor man's Pythagorean thing? No, right. It makes sense because no. It absolutely makes sense. It's not a poor man's anything because you basically want to you want to take that number divided by 2 for each component. So yeah, it's basically a fancy way of doing that. Yeah, that makes sense. And like we don't need a vector that points diagonally that way, I believe. Yeah, okay, sorry. No, I don't know what I'm saying, but I think I get it. Okay, let's do this. Copy. So pixel 00 location plus integer times pixel delta u plus j times pixel delta v. And then ray direction is camera center minus pixel center. Sorry, pixel center minus camera center. We make a ray that has camera center as the origin. This is the direction, right? And then we do ray color. And this is pixel color. Okay, I have no idea what this is going to print. Now I'm curious to see what this is going to print. Copy this. Okay, so const pixel center is... actually, you know what? Let's adapt this. Const pixel center is pixel 00 lock. We have it. Plus I... So for us, I is W. Pixel delta U. Yeah. I think this U should really be renamed to W in my case. But in any case, plus h times pixel delta v. No, that's fine. Okay, so this is the first thing. And this is R. Something like this. We might need an init function for Ray. Oh, we don't have Ray here. Okay. Okay. Let's fix this stuff. So we can't do this way. W needs to be splatted. So vec.splat h.splat. There you go. Right direction. This works. Pixel. Don't care. This is just going to be pixel. And it's ray color that for now is 000. Okay, so wait. As the code was given to us, this is right now not even implemented. So I guess we're going to implement it. I don't know. Function ray color. So this is what they had. Okay. We don't need this anymore, do we? Doesn't seem that we do. Okay, so let's see what happens now. Notice that in the code above, I didn't make ray direction a unit vector. Let's see. Okay. Because I think not doing that makes for simpler and slightly faster code. Now we'll fill in the ray color ray function to implement a simple gradient. This function will linearly blend white and blue depending on the height of the y coordinate after scaling the ray direction to unit length. Because we're looking at the y height after normalizing the vector, you'll notice a horizontal gradient to the color in addition to the vertical gradient. I'll use a standard graphics trick to linearly scale alpha between 0 and 1 when alpha equals 1.0. I want blue. When it's 0, I want white. In between, I want a blend. This forms a linear blend or linear interpolation. Yeah, which is the same formula. 1 minus alpha times start value plus alpha times end value. Okay. Okay. And so we expect to see this, huh? That's it. Okay. So unit direction is unit vector of r dot direction. So r dot direction we don't have. So it's vec dot unit of r dot direction. Wait, do we call it dir? Yeah, we call it dir. Okay. So this is this. Then const a is actually, you know what? Let's do it here. A is 0.5 times unit direction unit dir dot y plus 1.0. And then we return 1.0 minus a times vec.splat times I guess this is vec.once. I'm gonna make vec.1 plus vec.plot a times 0.5, 0.7, okay. I'm gonna make this a constant. I don't know what. I don't know what that is. Okay. So in vec, we had 1. Okay, I don't know what this is. I guess it's like a color it's the color that we're blending, basically, I guess. Because on yeah, I guess it's the color that we're blending, right? Okay. And so this should build. Okay, let's take a look at what build errors we have. Ambiguous coercion of division operands. Comtime int and comtime float. Non-zero reminder of in const h usize. Main does line 11. How do you like this? Incompatible types, comtime float, and usize. Okay, so this is in viewport width, right? Yeah. I think, by the way, if image, no, these are integers, that's fine. I guess, we can do this. Is this happy? Incompatible types usize and comtime float. Image height is usize. Well, what if we make it, is it usize? Yeah, because this is usize. If it was comtime int, would that make it better? It works. Let's see, mix scalar and vector operands. Vector and struct. Oh no. So I guess I have to explicitly either write at vector or we have to. Duh. No, there's no way we make a variable for this. Vec3 111, we already have vec.1. Next problem. Let's see. Ray does not support a reinitialization syntax. Yeah, that's true. That is something that left as a to do. Function init origin vec3 here vec3 returns a array. Pretty much. So where are we creating one of these bad boys? I don't remember. Line 60. Yeah, there we go. So array equals dot init. Next problem, accept F64 found usize. Vec 25. Come again, accept type F64. found U size. I guess we need to do two things in base on what we're given. Switch type of n, and we have U size return splat of at float from int n. And then we have f before return at splat n, else unreachable. Does this make everything happy? Reach unreachable code. Oh, we're passing to, okay, so U size, comp time int, f64, comma, comp time float. No field or number or function named y in vector. Yeah. So this is back.y of unit there. Okay. Well, success. Is this the aspect ratio that we want though? It looks mostly okay. It's just not 16:9. What did we forgot to do? What did we mess up? Like the blending is happening beautifully. We're just somehow forgetting something. I don't know. Oh, I know what we're forgetting. Wait. I think we're lying somewhere in maybe the file format. Are we lying? We're not lying. Well, we're saying 400 by 400. So there's something wrong. We think that the width is the same as the height. Why are we messing this up? We are doing the viewer you're using probably displays a scaled image. P3 header is width and height. Yeah, but regardless, we're passing in wrong numbers. We're giving 400. That's definitely wrong. We should be giving 400 something else. So width is 400, sure. This should be something else. This should not be. Let's do this. Add compile log h. Let's see what's h. Yeah, it's 400. Why does this give us 400? Oh, because of this. Oh, it's empty? Oh, we also need to remove the compile log. Somebody said that it's width then height. Is it? We're doing height then width, which previously did not make a difference. Now it might. It was width then height. Yeah. Thank you. We also were able to catch this right away. Thankfully. There we go. Okay. fix our problems. You're using minus 0.0 to cast to float? Yeah. Hell yeah. I am. I totally am. And you can't stop me. Although I agree, it's a poor man's way of obtaining a float, huh? Definitely true. Okay. So success. We are okay. We still have a way to go, but so far so good. The length of the programmer will go not to use as. I don't like using it as. Honestly, I get why it's there, and I can see. I'm not saying that it's categorically wrong to use it, but my personal preference is to always do something else than use as. I think that it adds way, way, way too much noise. So yeah. Let's see. Noticing the color above, I didn't make any right direction. Okay, we did this already. We did this. We did this. Adding a sphere. It's time. Let's add a single object to a ray tracer. People often use spheres in ray tracers because calculating whether a ray hits a sphere is relatively simple. The equation for a sphere is of radius r, that is centered at the origin, is an important mathematical equation. Yeah. You can also think of these as saying that a given point xyz is on the surface of the sphere. If a point is on the surface of the sphere, then x squared plus y squared plus z squared equals r squared. If a given point xyz is inside the sphere, then this value is lower than r squared. And if a given point is outside, then this is bigger than r squared. If you want to allow the sphere center to be at an arbitrary point, then the equation becomes a lot less nice. You subtract each component to each component. Okay. In graphics, you almost always want your formulas to be in terms of vectors so that all the XYZ stuff can be simply represented using a vectory class. You may know that the vector from point P equals XYZ to center C is C minus P. Yes. If we use the definition of the dot product, C minus P times C minus P gives us the formula. So then we can rewrite the equation of the sphere in vector form as C minus P times C minus P equals R squared. We can read this as any point P that satisfies this equation is on the sphere. We want to know if our ray ever hits the sphere anywhere. And if it does hit the sphere, there is some t for which pt satisfies the sphere equation. So we are looking for any t where this is true. So we plug in pt, okay? Which can be found by replacing pt with its expanded form. So c minus q plus td times c minus q plus td equals r squared. We have three vectors on the left dotted by three vectors on the right. Wait, we have three vectors on the left dotted by three vectors on the right. Oh yeah, so these three, yes. If we solve the full dot product, we would get 9 vectors. You can definitely go through and write everything out, but we don't need to work that hard. If you remember, we want to solve for t, so we'll separate the terms based on whether there's a t or not. Okay, so you do some math, and we move the square radius over to the left-hand side, and oh no, what? It's hard to make out what exactly the equation is, but the vectors in R in that equation are all constant and known. Furthermore, the only vectors that we have reduced to scalars by dot, the only vectors that we have are reduced by scalars by dot product. The only unknown is t, and we have a t squared, which means that this equation is quadratic. You can solve for a quadratic equation in this form by using the quadratic formula. So solving for t in the ray sphere intersection equation gives us these values for a, b, and c. Okay, a is d squared, b is 2d minus cq, c is c minus q times c minus q minus r squared. Okay. Using all of the above, you can solve for t. but there is a square root part that can be either positive, meaning two real solutions, negative, meaning no real solutions, or zero, meaning one real solution. In graphics, the algebra almost always relates very directly to the geometry. What we have is no solutions, no intersection, one solution touching, just barely touching, two solutions, full intersection. Sure. Creating our first ray trace image. If we take that math and hard code it into our program, we can test our code by placing a small sphere at -1 on the z-axis. So the z-axis is the depth axis, and placing it at -1 should put it in front of us. I'm assuming that you want the sphere to be in front of us, but also, should it be minus? Isn't positive in? No, it's positive out. Is it? Let me scroll up for a brief moment. No, it is positive in. So why are we placing it at -1? Oh, is it because we ourselves are on the way back? Are we inside the sphere? What's going on here? Okay, well, let's start doing this. And then in ray color, if hit sphere, then return color 1. Okay, so this is showing us where that happens. You can only see what is behind the viewport plane. Hmm. Okay, let's see. OC. Um, OC is a vec3. And we subtract our dot origin. So yeah, that works. A is doing a dot product. So this is a vec dot between two vectors, r direction and r direction. Yes, we're squaring. That works. Then const b is we need to vec splat. Times vec dot direction NOC. So that works. Then const c is vec dot dot times radius minus radius times radius. Where's radius though? Where is radius defined? Oh, it was up there. Do I still have? Oh god. Okay, that's on me. But this means that this needs to be splatted. Dot returns a scalar. Oh shit, you're right. You're right. And so we don't need to splat anything. Yeah. You're right. Whoops. Is it possible to use Zig's build system to make a step that pipes the output of run step directly into an image? Yes, absolutely. You can do capture standard out. You can also capture standard error, and then you can decide what to do with it. You can test it for equality against a known good value. For example, you can write it to a file, and then you can install that file somewhere. Honestly, in this case, I would probably change the main function to write to a file instead of standard out. But for now, like that's what I would do. But for now, I'm just following what the book does. Okay, so this is its sphere. And yeah, good point that the dot returns a scalar value. I forgot. Okay, so we do this in right color. If hit sphere, if hit sphere, then return this. Okay. Let's see. Vector 334 is not a function, right? We can't do r.origin. This is vec.origin r. Although no, wait, we can do it with. Wait a second. No, r is ray. It's not this. Wait a second. Where are we doing it wrong? 80. r.origin. But that's ray, so we can do it. What's going on? Type vector 3 f64 not a function. Did I typo it? No, I said that r is array. Origin is not a function. Oh, you're right. Oh my god, yes. This is now me going insane. And you know what? I think I want to call direction at this point. Calling it dir. Okay. There we go. We got our fancy Japanese flag. Success. Okay, next. Surface normals. Oh wait, these like sort of things, all sorts of things like shading, reflection rays, and more than one object. But we are closer to halfway done than we are to our start. One thing to be aware is that we are testing to see if a ray intersects with the sphere by solving the quadratic equation and seeing if a solution exists. But solutions with negative values of t work just fine. If you change your sphere center to be z equals +1, you will get exactly the same picture because this solution doesn't distinguish between objects in front of the camera and objects behind the camera. Yeah. This is not a feature. We'll fix those issues next. Okay. Shading with surface normals. First, let's get ourselves a surface normal so we can shade. This is a vector that is perpendicular to the surface at the point of intersection. Yes. So you need to basically make a vector from the center of the sphere. Yeah, your 2 points are center of the sphere, point of contact, line that goes through it. And that's your normal. We have a key design decision to make for normal vectors in our code, whether normal vectors will have an arbitrary length or will be normalized to unique length. Ooh. It is tempting to skip the expensive square root operation involved in normalizing the vector, in case it's not needed. In practice, however, there are 3 important observations. First, if a unit length normal vector is ever required, then you might as well do it upfront once, instead of over and over again, just in case, for every location where unit length is required. Second, we do require unit length normal vectors in several places. Third, if you require normal vectors to be unit length, then you can often efficiently generate that vector with an understanding of the specific geometry class in its constructor or in the hit function. For example, sphere normals can be made unit length simply by dividing by the sphere radius, avoiding the square root entirely. Yo. Okay. Given all of this, we will adopt the policy that all normal vectors will be of unit length. For a sphere, the outward normal is the direction of the point minus the center. Yeah. Disclaimer, newbie Zig build system user here. Is there any project that can help transition from a horrible Visual Studio solution projects in C++ MSVC to a nice build.zig? So There is no self-contained resource that I know of, but here's two things that you can do are RKTR. Number one, so I'm taking a brief break to answer from the ray tracing stuff to answer this question. So here are two things that you can do. Actually, let's say three things. Number one, go to zigline.org, learn, and then there's a Zig build section. This will teach you some things about the build system. Bork, send this. Then resource number two. And this is actually, you know what? I'm saying that this is resource number two, but I think this is more basic than actually what's written on the website. So you can go to Zig build system. Oops, I typoed it, but should still work. I made a video that explains the basics. This also can help. Third, you can go to github.com/allyourcodebase. This is an organization that has right now 93 repositories of C and C++ projects that were packaged for Zig, well, using the Zig build system. Not every package is of maximum quality, meaning that in this organization that I run, people are allowed to push projects that they package, that they made a build system, a build.zig for, even if they don't port everything right away. Like maybe sometimes people only need a subset of what the original project was able to do through the build system. And so they only port that part that they need, and that is fine. So my point is, not every project will show you how to do everything A to Z, but each one of them does actually tackle a real world C project, and so C or C++ project. And so you can actually see how that works. For example, Tracy is a C++ project. Most of them are just a build script that adds the original project as a dependency. Some of them are a fork of the original project, depending on their needs. Some of them need to apply patches, for example, or make changes to the original code. So I'm going to link you this. This is going to be your last resource. Let's see. Raytracing is working on something similar, but it needs some cooking. Oh, you mean some automated stuff? That also works, but you know what? Just learn how to use the Zig build system and port everything over, get used to it, and you'll never look back again. You'll never look back to CMake again. So save yourself. Remove the dependency, because at the end of the day, you're doing some work. You might as well do the work in a way that allows you to get rid of the dependency completely. And all you do is, and at that point, you're just left with one dependency, the Zig build system, the Zig compiler that does build system and, compiler. Thank you for the $5 to the ZSF. Thank you very much. Okay, so let's continue. Okay, so this is our normal. Let's see. On the Earth, this means that the vector from the Earth center to you points straight up. Yes. Let's throw that into the code now and shade it. We don't have any lights or anything yet, so let's just visualize the normals with a color map. A common trick used in visualizing normals, because it's easy and somewhat intuitive to assume n is a unit length vector. So each component is between -1 and 1. So it is to map each component to the interval from 0 to 1, and then map it to XYZ. Okay, let me think about it for a moment. Yes, because it's a unit vector, it does go to from -1 to 1. Yes. Okay, so we scale it that between 0 and 1, and then we scale that to 0 to 255. For the normal, we need the hit point, not just whether we hit or not. Yes, which is all we're calculating at the moment. Yes. We only have one sphere in the scene, and it's directly in front of the camera, so we won't worry about negative values of t yet. We'll just assume that the closest hit point, smallest t, is the one that we want. These changes in the code let us compute and visualize n. Okay. So, hit sphere. If the discriminant is lower than 0, we return. So this now returns a float, and it actually computes the solution. And okay. So in here, We do this. If discriminant is lower than 0, return -1. If this is not a bool anymore, now this is an F64. Otherwise, return -b minus. See, Zig doesn't know what the heck. What the heck are you doing here? Yeah. So do we have our own SQRT for to do stuff? But discriminant is just a number, so no, this is just at square t. Do we need to change anything? I don't think we need to change anything. I think this math is good as is. Okay. And then in ray color, we do this. Hit sphere. You know what? Also having .init could be nice here, but nah, the curlies at the end of the day are shorter. Okay, if t blah 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 const n vec3 unit vector. So this is vec.unit for us. Once a vec3. So let's see. R at t gives us a vec3, and we subtract that to another vec3. Okay, and then we return 0.5 times color, but color is just a constructor for a different vec3. So we splat 0.5 times times vec3. I guess we have to do this. And we can't do n.x. Unfortunately, have to do vec x n vec y n. Why are you adding +1 to each component manually? Dude, I'm just copy pasting. I just copy pasted this thing. Do you think we should do what? Is this a reduce? Wait, what would be the operation that we should do to optimize this? Mul add, right? Okay, let me use mul add because I copied pasted your code earlier, but I never used it myself. So return, let's see, add mul add. Focused fused multiply add, similar to a times b plus c, except only rounds once and is thus more accurate. Supports floats and vectors of floats. So it's a times b plus c. So that would be n times 0.5, which needs to be splat. Also has type, so vec3. And vec.splat. And then we do plus 0.5, right? Because we do the +1. Here we're doing the +1 before. Here we're doing the +1 after. And that also needs to be splatted. Okay. So does the math sound right? Just splat works here because it has a result equation. Oh, you're right. We can use the easy splat. So this one. Although it doesn't make a big of a difference, right? But yeah, that makes sense. Okay. Cool. Okay, so we have this. And okay, it should give us this. Does it? It doesn't. Give us compiler error. What? We got lied. Let's see. Mixed scalar and vector operands. Vector 64 and struct. Okay, yeah, sure. There you go. This does not look right, does it? I mean, there's some gradients happening, I think, a little bit, but it's definitely not correct. Isn't mul add wrong here? Let's see. So this is doing each component, a vector where each component is +1. I guess this would be basically n plus splat of 1 and then multiplied by 0.5. Mul add does a times b. So first we divide, sorry, we multiply by, well, we divide by 2 basically. And then we sum c. And since we're taking the sum out, we're doing it after, then we 1 times 0.5 is 0.5. So we, instead of adding 1, we add 0.5. So this formula seems fine. But you know what? So I think that the fact that we have a different solution is because of something else. Yeah, so this gives us the same result. So these two things are equivalent. This is fine. But we might be doing something else wrong. Yeah, because this is clearly very different. Clearly very different. So what are we doing wrong? What are we doing wrong? Also, this code has all, this math has all the parentheses possible. So this shouldn't be a problem. Also, this is minus b minus sqrt. Yeah. Divided by 2.0 times a. Are we getting a different order of operation here? Maybe b times b minus 4ac. Is this stuff implemented differently in Zig than for them? I don't think so though, because then this would fuck up our intersections. We wouldn't even see. Wait, okay, so wait. I know what the answer is. We can reason about this. We are getting the sphere stuff is right. What we are getting wrong is how we end up dealing with the normal, right? No, we do not ignore basic mathematical order. Okay, so yeah. In any case, this was certainly not it. The problem is it's the normal vector. We are doing something wrong with the normal vector. We're doing. Let's take a look at this code here. Maybe this gives us a hint. It's unit vector of ray at t. T is the point where we touch the sphere. T is the point where we touch the sphere. And then we subtract. Why are we subtracting this 0, 0 minus 1? We're subtracting, I think, the center of the sphere, right? And this is what giving us the normal vector in theory. And then we scale it. Maybe we should print some of these values. I don't know. Let's see if at t makes sense. What if this is wrong? Wait a second. Wait a second. Andrew. uh, uh, don't worry, I'm joking. It happens. So we're doing fine. Okay, let's see. What's wrong with this malad? Let's take a look. By the way, I copy pasted it earlier without thinking deeply about it. Maybe it's time we do that. So here we're doing origin plus this multiplication. And yeah, that's a problem, right? We need to move direction last. Oh, as one way of solving it. Yeah. Okay. Or not? That wasn't it. Wait. You need the origin last. Oh, you're right. Origin is the thing. Right. Yeah, yeah, yeah. Oops. Well, at least we got to see an interesting image. There we go. Let's take a look at what it was. What the heck? That was cool. That's nice. There we go. Okay. Cool. So next, simplifying the ray sphere intersection code. Let's revisit the ray sphere function. Yep. Okay, so this is the same code as before. Nothing has changed. First, recall that a vector dotted with itself is equal to the square length of that vector. Okay, yes. Second, notice how the equation for b has a factor of -2 in it. Consider what happens to the quadratic equation if b equals -2h. Notice how the equation for b has a factor of -2 in it. Wait, what does that mean? Has a factor? What's a factor? Is that a component of dynamic multiplication? It's multiplied by -2. Um, yeah. Is this because of the -4? Is that what we're talking about? Is a factor a like I'm having a terminology problem right now. Are we having is a factor a component in a multiplication? That's what it is, right? Let's see. Continue the rest to the quadratic equation if b is -2h. So if it's -2h, then yeah, you simplify and you get that the 2's simplify out, and then you get h plus minus square root of h squared minus ac divided by a. This simplifies nicely, so we'll use it. So solving for h, b is -2d times c minus q. H is b divided by -2 equals d times c minus q. Using these observations, we can now simplify the sphere intersection code to this. I have to be honest, I have not really followed this math. But I trust the book. So let's see. It's direction minus length squared. Oh, it turns out that we do need length squared, huh? As a separate function. Okay, let's see. Vec3. So length, which we call magnitude, is this. I'm gonna call it magnitude 2, maybe. Thank you. Have fun. Okay. So let's take a look at this math now. So we have A. A is now this is different for us. This is vec dot magnitude 2 of this. We have h const h equals vec dot dot between r dot direction and oc, which is the one up above. Yeah. Then we have const c is oc dot length squared, so it's vec dot magnitude 2 of oc. Discriminant is h times h minus a times c. Okay. You did it too much, did I? Oh shit. Oh, you're right. Thank you. Ooh, that would have been bad, wouldn't it? Thank you. Holy cow. Thank you. Okay. Well, that sounds good. But now we don't have B anymore. So how did this stuff become? It's H. Okay. It's H. Okay, we're basically multiplying by 2. Okay. So H. There we go. Okay. So the idea is that they should yield the same result. Oh no, it does not. Not at all. Uh-oh. Wait. Where's my stuff? That did not work. It seems. Let's see. What did we change? We pretty much only changed the heat sphere. So this should be the same exact thing. So it's on us. We didn't change anything else, did we? Literally nothing else changed. So what are we doing wrong? Is this the correct implementation of magnitude squared? Yeah, it's the dot product of V plus the dot. Wait, it's the dot product between V and V, right? And then you sum it. H not minus H in the equation. Oh, thank you. Thank you. Yeah. Okay, we're back in business. Thank you very much. Yep, works. Okay, an abstraction for hittable objects. Now, how about more than one sphere? Well, it's tempting to have an array of spheres. A very clean solution, like clean, is to make an abstract class for anything that array might hit and make both a sphere and a list of spheres just something that can be hit. What that class should be called is something of a quandary. Calling it an object would be good if not for object-oriented programming. Surface is often used. Well, we don't have objects. We don't give a fuck about objects. So we could very well call our stuff object in the physical sense of the term. And you know what? I think I'm going to do that. With the weakness being maybe that we would want volumes, fog. Name it object. Yeah. Hittable emphasizes the member function that unites them. I don't love any of these, but we'll go with hittable. Well, we're going with object. Why not call it physical object at this point? I just call it physical object. If object alone is not enough to specify what kind of object we're talking about, physical object should solve it. I think it's better than hittable. In any case, this hittable abstract class, Jesus, will have a hit function that takes in an array. Most ray tracers have found it convenient to add a valid interval for hits, tmin to tmax, so the hit only counts if t is between tmin and tmax. For the initial raise, this is positive t, but as we will see, it can simplify our code to have an interval tmin to tmax. One design question is whether to do things like compute the normal if we hit something. Wait, what? One design question is whether to do things like compute the normal if we hit something. We might end up hitting something closer as we do our search, and we will only need the normal of the closest thing. I will go with the simple solution and compute a bundle of stuff. I will store this instruction. I have to be honest, I do not understand what this sentence is supposed to communicate. Here's the abstract class. One design question is whether to do things like compute the normal if we hit something. So you hit something, and the question is, do we compute the normal of that hit or not? Oh, I think I guess. So, okay, I think I'm starting to understand. He's talking about abstractions, and his question is, should the hit abstract method interface thingy concern itself also with computing the normal of that particular hit? Or should we leave that for like that responsibility for something else? Well, if I know anything about clean code, is that one class should have one responsibility and only one. So if your thing is hit and it's also completely normal, then you're not following the something separation of thingies principle, thus you're doing bad OOP, and you're gonna go to OOP hell where everything is functional programming. Single responsibility principle. Thank you. Separation of concerns. Wow. Okay. So he doesn't know whether to compute the normal in here or not. What did he end up doing then? I will go with the simple solution and compute a bundle of stuff I will store in some structure. Okay, so a hit has the point where we hit, the normal of the point where we hit, and I guess whatever normal of whatever surface. I guess it depends on the concrete shape that we're hitting. And then there's also double T. And T is our... I actually wouldn't know how to describe T at this point. What is T? I'm not sure. Yeah, I'm not sure how to describe T. The other two I get. It's time, isn't it? Yeah, I guess. Yeah, it's distance from an eye. Yeah, that makes sense. The length of the ray. Yeah. That makes total sense. Yeah, it's distance from the eye. Yeah. Okay, cool. Okay, so hittable. Yeah, the fuck is this shit? What do I do with this? Now, what do I do with this? How do we solve this in Zig? How do we do it without object-oriented programming? Oh no, we're never gonna be able to solve this. Let's see how they do a sphere then. They give it the sphere a hit method. So I think we have two options here in Zig. One is our list of objects going to be objects in the physical term of the word? Okay, so in Zig, when I'm going to say objects, we literally mean here's my mouse object. Okay, no abstract objects in here, only physical objects. So the question is my list of objects going to be com time known, or is it going to be dynamic? Your shapes will be a well-known list. Then, if that is the case, we can get away with just comp time duck typing. We make a bunch of different structs. They share absolutely nothing other than the fact that they all happen to have a hit function that you can use on them that has the same signature. Actually, it doesn't even have to have the same signature necessarily, but obviously it makes sense for it to have. Why not a tagged union? Yeah, we could also do a tagged union. Sure. But here's my point. So, Lee Cannon, you are totally right. So I guess we have three levels of abstraction, right? Wait a second. Wait 1 second. Wait 1 second. I have a drawing tablet. I almost forgot that I had it. I guess now it's time to whip it out. That doesn't sound good, but I said it. Lorian. Yo, my calligraphy is still gonna be crap, but we have this. Okay, so let's see. Why not attack union? Dynamics dispatch, static dispatch, in and dispatch. Yeah, as a rustician would call them. Yeah. So this is the idea exactly. So the idea is you have basically 3 levels of dynamicism. And by the way, this is in my opinion something, one of the most genuinely interesting about software development. I think that this is one of the things that as a software engineer, one of the big questions that you have to answer every time you make something. And the fact that we're bad at answering this question really speaks poorly for our industry. So think about it. Every time you make a piece of software, you have to choose the level of dynamicism, like the dynamicism level. And so in our case, we have the tools at our disposal because we can say like level 1 is duck typing. So duck typing means we have no real dynamicism. We use comp time reflection to basically inline the call to the correct function based on. We're basically using metaprogramming. We're using metaprogramming to just make it more easier for us, more syntax sugary, to have a completely static set of shapes that we want to apply operations on. Then we have enums. Well, no, not enums. Sorry, that's more like a Rust word. It's tagged unions. Oops. Let me try again. Yeah. Oops. How do you hold this thing? Yeah, tagged unions. And this one is more dynamicism because now you dispatch to a runtime function call, but among a closed set of possible destination functions, the ones that are in the tagged union. And this is actually often enough, and you don't need any more than that. And I think that this methodology, maybe not today, but I suspect that this approach could potentially give you optimizations that you wouldn't be able to get with the fully open-ended vtable approach. I'm not sure though, but I think it might be possible. So 3 is vtable. Oh, G? Why there's a G there? Yeah, vtable. And I think it's interesting because you have these 3 clear different levels, right? And each come with more flexibility, but also with different kinds of performance trade-offs. And I think, this is just one example where this happens. But if you think about it, every time you write a piece of software, you have to choose the level of dynamicism of it. You make a tiny program that computes the sum of 2 numbers. You can hard code the numbers, and then the program always prints the same value. You can hard code one of the 2 numbers and leave the second one as an input that the user can give. That's more dynamic. You can have both numbers be given by the user. You can have the operation be provided by the user. Maybe it's not a sum, it's a multiplication, it's a division. Then, you can let the user come up with not just a single operation, but multiple operations. And all of these choices have implications. And the same is true for pretty much everything that we make. And it's kind of weird if you think about it, that we have programming languages that take this gradient completely away from us, and they make a choice for us. And what happens is that they tend to give us the highest possible amount of dynamicism, even though we might not need it. And one thing that I realized while working on a tiny set of programming languages myself is that if you're not careful, so for my static site generator, there's a templating language and that has a tiny scripting language. And, even though it's tiny and extremely self-contained, it is a tiny programming language. And one thing that I realized is that dynamicism in this type of programming language is what you get by default if you're not careful. If you're not careful, your functions will be able to accept any parameter, return any parameter, have a lot of dynamicism to them. But all of this dynamicism costs you, because then it becomes harder to do, for example, static analysis, because if a function can accept any type of argument, like maybe you even define it as that, where maybe you make a function that can accept maybe a string, maybe a number, maybe something else, and it behaves differently based on what you pass in, then all of this stuff makes it more complicated to do, as I said, static analysis, provide tooling for it. But one thing that I noticed is that you don't get to dynamicism by being good at designing programming languages. You get to dynamicism by being bad. It took me a moment to realize that that's where I was going and hit the brakes and stop. So in any case, I thought this was something interesting. Let's see, you want an array of hitables, so you can't really use duck typing alone unless you have each array for each object type. No, you can. So here's how it works, Cannon. The way you can make it work is that you can do something like this in your well, I'm going to do it in the main function, I guess. But in your main function, you can do this. You can do const shapes, objects. And then you do this, and you do, cube 1, cube 2, pyramid, sphere, and then you semicolon. And this can be different types. And then what you do is you do inline 4. And then you do obj.hit. So you can totally do this. The way it works is that this is not really an array. This is a tuple. This is a comtime known struct that you can iterate on, basically. Yep. Let's see. Fourth, separate array for each type of object is best approach here. It would be even faster than a union. That's a good point. So you're saying we do want some dynamicism, but also we know that there's a fixed number of types of objects, and so you just make a list for each type. That's also fair. Yeah. But I'm going to go with the full comp time stuff, I think. And then, but this is a very good point. We can go with the full comp time stuff. And then if we need something more, we can then switch to multiple arrays. Yeah. But I think that so far, like just one array like this is going to be fine. I guess this approach is in case you have many, many functions. Like if you have a lot of functions, then maybe it might be worth. I will definitely, at some point, will definitely be worth having multiple arrays so that you can use for instead of inline for. Okay. Yeah, it's comp time dispatch. But think about it. Inline for, you should think of inline for as literally copy pasting the body multiple times. When you have a normal for, you can have actual go to, etc. Well, I shouldn't say go to. I should say, you can have actual looping, actual jumps in the code instead of having the body be copy pasted n times. Branch predictor won't be able to predict which type of object you're trying to intersect with. I think I'm not communicating properly than what we're talking about. I'm talking about this approach, but with the difference that you do, like, first you do all spheres, then you do all cubes, then you do all pyramids, and that reduces code bloat. If you have a ton of these things, that reduces code bloat compared to what I showed earlier when you do inline for. Not doing inline for will save you some code bloat. Okay. Let's go back to ray tracing in a weekend. So what are we doing here? Okay, so this is the implementation of the sphere, huh? Okay, let's do this. Let's make new write source / objects.zig. Yeah, okay, so we're gonna put them here. So const sphere, the struct has a radius probably, I'm guessing. Does it have a position? I guess it has maybe a position. So let's get also vector in here. You know what? Let's get all of vec and then we get vec3 from it. Okay, so has a center, which is going to be a vec3. By the way, I'm not looking at the code, I'm guessing, but this seems not too complicated. So function. Nothing prevents you from using inline for in this approach. Sorry, I'm not looking at the code, but if your code is this one, my point is that at some point you don't want to use inline for. At some point, if you have 100,000 shapes, as an extreme example, you do not want to use inline for. It produces code bloat. You want a normal for. So my point is that not using inline for and still being able to do static dispatch is what you want to achieve when you have a ton of shapes. I'm sorry, when you have a ton of objects. So sphere, hit, I don't remember the signature of hit, and it returns a hit, right? So we have to define what a hit is. So a hit is, we said, the hit position, which is a vec3, then the normal, which is a vec3, and then the T, which is an F64. And that's a hit. Okay, so hit takes in a array, tmin, tmax. Okay. I guess I'm going to copy this. Some of this is what we had earlier. Some of it it's new. Well, okay, you know what? Wait, let me get the signature right first. Const override. No, I'm not talking about different types of objects. I'm talking about you still have only circles, squares, pyramids, let's say, but then you have a ton of those. But then you have many of those. Just a lot of objects is obviously won't produce code bloat. Um, if you have one array with a mixed set of elements, it will. You want to align for over each object? I think we're talking past each other. Give me a second, I'll show you. Let me get there. So S is sphere, R is ray, T-mean is an F64, ray T-max is an F64, hit record and returns bool. So yeah, no, exactly. So what I'm saying specifically is this: you can do the lower one, and to do the lower one, you have to do inline for. But then if you have a ton of these, like if this tuple here is gigantic, you don't want to do it anymore because that will produce a ton of code bloat. So then to scale up to a ton of things, you want to switch from this to this above, which I believe is what Andrew was suggesting originally. And yeah, this above is pretty good because it allows you to do four. You do four on box, then you do on all boxes, then you do four on all circles, and that reduces code bloat significantly compared to doing inline for on a gigantic list like this one at the bottom. So this is returning Boolean and then modifying a value. Do we want this? I'm not sure we want this. Why? What is wrong with just an optional hit? Is it a problem for us to do an optional hit? It doesn't seem to be a problem for me. Let's do the optional hit for us. Do we need this? Yeah, this is fine. So okay, so we need to do the math, which is what we were doing here. But then it's doing something more because it's also computing the normal. So we do this, we do the discriminant. If the discriminant is below 0, we return null. So early return. Then find the nearest root that lies in the acceptable range. Okay, so this is different than before. So let's do this. Let's see. Root is h minus sqrtd. Where is that? Oh, I failed to copy this. Okay. So divided by a, if root is lower than or tmax is blah, blah, blah. We're making root a bar. Return false. Let's see, what if rec is changed regardless whether the hit returns true or false? Oh shit. But no, that's not what's happening. We only modified down here. I don't know why they use this style. I guess it's because nullables are probably considered an advanced C++ feature. So they decided to use this approach because they didn't want to use optionals. No, but I think that depending on the usage of this API, it could have been a thing, but apparently it's not. Okay. So here we do return dot t equals root dot p equals r dot at rec dot t and dot n equals rec dot p minus center divided by radius. I haven't checked if these operations make sense for us or not yet, so just translating. Okay, let's like type check, or you know what, we let Zig type check this stuff for us. So here's the problem: center origin, and there's no center for us. Yeah, we were getting center. We're not getting center here. What's center? What? Center is our center, and radius is our radius, right? So this is as.center, and this is yeah, you know what? There's too much stuff called R. So radius. Let's call it radius. Now this is rec, because rec was called what? What's rec? Oh, rec is the return value. Okay. There we go. Okay. So this should be our sphere, I guess. Note that here we use C++ standard function std fmax. What? Where is fmax? Sphere. Public sphere is given a center and a radius is, what am I looking at? Is this a constructor? And it's constructor initialize list. So this is setting these fields, and radius is being, if radius is negative, we give it radius 0. What's going on here? Which returns a maximum of 2 floating point arguments. Similarly, we will later use fmean, which returns the minimum of the 2 floating point arguments. Why are we creating negative spheres? What's going on? Why are we creating spheres with a negative radius? Actually, that's my question. What's going on? It's defensive programming. I see, but if it is defensive programming, it's kind of stupid. Like Andrew is right. Like you should assert. You shouldn't. They don't know what an assert is. That's the problem. They don't even know what a freaking assert is. Okay. God damn it. You know what? Let's even take it out of std debug. Let's just answer right away. But it's like, it's the dumbest possible kind of defensive programming. Or maybe not. Yeah, I think it is the dumbest. Like, okay, either you're not doing any defensive programming, so you're just letting arguments potentially violate invariants. Yeah, that's fine. Should we allow a radius 0 sphere? Maybe. Or you know what? Maybe they're gonna use some kind of random number generator later on, and they just don't want to bother with the fact that sometimes it gives you negative numbers, and so they don't want to worry about having to make them absolute. But then again, why clamp them at 0? Then you would want. Then I think you would want to just do the up. Whatever. Okay. Whatever. Okay. Sure. There won't be negative radi. Then why is there? Then why is that function called there? God damn it. The second design decision for normals is whether they should always point out. At present, the normal found will always be in the direction of the center to the intersection point. The normal points out. If the ray intersects the sphere from the outside, the normal points against the ray. If the ray intersects the sphere from the inside, wait, how does it do that? To intersect the sphere from the inside, it would have to first intersect it from the outside. I'm guessing this has to do with the fact that we're picking these at not exactly at random, but like we're not really too discerning with how we pick our t, and so sometimes we could pick the solution that makes us intersect towards the outside. The sphere can be so large that it's around the eye. I guess technically that would also be an option. But no, because, I mean, I guess yes, but also it would be I think it would be a degenerate case, because you would, like the sphere, it's not, the way we consider hits, I believe, the sphere is not like empty. I might be wrong. No, you know what? I might be wrong, because I think we only consider solutions to the equation, so we only do surface. Foreshadowing glass spheres. Yeah, that makes sense. Okay, if the ray intersects the sphere from the outside, the normal points against the ray. If the ray intersects the sphere from the inside, the normal, which always points out, points with the ray. Alternatively, we can have the normal always point against the ray. If the ray is outside the sphere, the normal will point outward, but if the ray is inside the sphere, the normal will point inward. Possible directions for sphere surface normal geometry. Outside surface, inside surface, this is the ray. Which normal do we pick? Yeah, I don't know. But in any case, if you always compute the normal as point and then center of the object, then you can always make it point outwards, I guess. I guess there are reasons instead to try to point it the same direction that the ray is pointing at, maybe. Right? That would be the only reason why you would even worry about this, because if that wasn't interesting, like if you were fine with a normal always pointing outside, then you kind of get that for free just by computing that from the center, I think. In any case, we'll see. We need to choose one of these possibilities, because we will eventually want to determine which side of the surface that the ray is coming from. This is important for objects that are rendered differently on each side, like the text on a two-sided sheet of paper, or for objects that have an inside and an outside, like glass balls. Yo, that foreshadowing, man, on point. Not too far into the future, not too close, just the right distance. Good job. If we decide to have the normals always point out, then we will need to determine which side the ray is on when we colorate. We can figure this out by comparing the ray with the normal. So this means with the normal, as in the normal always pointing out, I'm guessing. If the ray and the normal face the same direction, the ray is inside the object, yes. If the ray and the normal face opposite directions, then the ray is outside the object, yes. This can be determined by taking the dot product of the two vectors, where if their dot is positive, the array is inside the sphere. Because they're either both positive or they're both negative. While if they point in different directions, then one of the two will be positive, the other one will be negative, and so their dot product gives a negative solution. Okay. If we decide to have the normals always point against the ray, we won't be able to use the dot product to determine which side of the surface the ray is on. But why are we... I'm not sure I understand this reasoning, because in my mind, we're computing normals. Wait, how are we computing normals up until now? Maybe I should have paid more attention to the math that we're doing, because that maybe would explain it. Where's n? I mean, it's point minus center divided by radius. So it's not even a function of the ray. So why are we wondering about that? Well, I mean, no, it is. I mean, sorry, the ray is in the picture, I guess. But I mean, that only gives us a point. So I don't get it. Like the directionality, I don't get it. In any case, also, wait a second. P at. That gives us a vec3. Center is a vec3. So this gives us a vec3. And then we're dividing it by radius, which, last I heard, is not a vec3. So, yeah, right. Because we need to splat this bad boy. Okay. Instead, we would need to store that information. Okay, but fair. But so far, I'm not sold at all on why we would do it that way. So I'm not invested in the resolution so far, because to me it seems clear cut that we want the other one. Now watch me get completely destroyed. P is the intersection point, so P minus center is vector outside the sphere. Yeah, that's my point. Like, my point is that since we compute it this way, how will we even compute it the other way? Like, I don't get it. Anyway, we can set things up so that normals always point outwards from the surface. Isn't this already happening? God damn it. Or always point against the incident ray. This decision is determined by whether you want to determine the side of the surface at the time of the geometry intersection or at the time of coloring. In this book, we have more material types than we have geometry types. So we'll go for less work and put the determination at geometry time. This is simply a matter of preference, and you will see both implementations in the literature. Okay. We add the front face boolean to the heat record class. We'll also add a function to solve this calculation for us, set face normal. For convenience, we will assume that the vector passed to the new set face normal function is of unit length. We could always normalize the parameter explicitly, but it's more efficient if the geometry code does this, and it's usually easier when you know more about the specific geometry. By the way, where's the assert? Dude, you could assert this. Like, this is a perfect case where you can ask to have for correctness. You're saying, I'm assuming there's this implicit invariant. Please put an assert. Make it an assert. God damn it. Okay, let's go do this, and let's do it the right way. So we're saying that hit also has what's it called? Front face. It's not that easily to correctly assert that. I mean, you can assert that it's like within a given delta, right? Let's try to make this work. Let's see how it works. So front face, bool, and then what did they do? Set face normal. Front face is the dot, and then based on front face, normal gets negated. Wait, now I'm... Now I'm confused. Now we're flipping the normal. Why are we flipping the normal? Isn't the normal always pointing out? So I guess this makes the normal point in the same direction as the ray? Yeah, I get that. But, and then, so we're not happy with that anymore. So maybe I missed a piece reading this. So we're not happy with having the normal always point out. We want to have the normal, we want to have the normal also, we want to be able to have the normal also follow the ray. I guess that's the point. I feel like this explanation above spent too much time arguing for a way of computing this that we didn't go for at all. So I don't find this case compelling. I get the point that you might want to know about this because that's what you might find in literature, fine. But the whole like argument, should we decide to do this? Like this what? Like what we're doing so far seems perfectly fine. In any case, okay, so now we want to be able also to flip the normal. Fine, let's flip the normal. Set face normal. Okay, I'm gonna copy this so we can have it for reference. Okay, so pub function set face normal. We need to mutate it. And we have outward normal. Isn't this n? I guess no, because we were modifying n. So like if you call this once, then n is going to be flipped. But imagine a plane. Okay, I'm flying in the sky. I'm in a Boeing 747. Hits normal. I'm joking. Okay, imagine a flat plane or like an horizontal one. Its normal will show, for example, up. So we hit the plane and the normal points up. But if you look from the bottom towards the plane, you want to have the normal to be down. Understood. Okay. So you need fields properly. What do you not like about P, N, and T? P, N, T. No, I think the song was slightly different than this. Outward, normal, like 3. Set face normal, void. Okay. Okay. Note the parameter outward normal is assumed to have unit length. Okay, so here's how we do it. If const built-in equals at import built-in. By the way, I think that built-in, this is not going to happen too soon probably, but I think that built-in is going to be renamed to config, which I think it's a much better name because it's like your build configuration. So don't take what I'm saying for granted, but I think it might happen. It's just that probably requires messing with a bunch of stuff that's hard coded. That's probably kind of brittle right now. So if built-in dot I don't remember. Let's go to definition. Target OS single threaded DBI CPU output mode. Where is it? Mode built-in dot mode is dot debug. If we are in debug, then we spend some extra effort computing stuff. So I could put a normal assert. The point is I want to make sure that the assert just runs in debug mode. So also the extra like calculations. So So we're basically what we want to assert is that this outward normal is already of unique length. So we do LVM should be able to optimize it. Yeah. Andrew, have you seen the thread on Zigit? There's like some cases where it's kind of obvious. No. I don't want runtime safety. I don't want to run this in release safe. This is, by the way, an interesting point. Because, and by the way, this is like up to taste in a sense. There is a difference between wanting to have something happen only in debug, happen in runtime safety mode, so like release safe, and not happen at all in release fast. In the case of Zine, for example, I have some extra turbo redundant safety checks that I don't even want to have in our release safe mode. And I personally believe that in the case of a ray tracer that for some reason you want in release safe, you want to build in release safe, which honestly I would never build in release safe. It's to me it's either debug or release fast, I guess. Although I guess maybe you can do that because you're testing and you still want it to be not too slow while testing it, I guess. But in any case, there are some stuff that you could generally want to only relegate to debug. I do that on purpose sometimes. So you can totally do the debug runtime safety. That's fine. That's precisely not what I want to do right now. So outward normal. So we want to compute basically the normalized version. How do we do that? I don't remember. What's the name of this function? Unit, right? Okay, so const unit equals vec dot unit of outward normal. And then we need to assert that the two are pretty much the same. So how do we make this happen? I guess we can subtract them and assert that it's close enough to 0 with a delta that we pick. That sounds right, no? I mean, at the end of the day, even if it's not normalized and it's close enough, who can even tell the difference? So we say assert, const delta is unit minus outward normal. And then we say, how do we do this? Contains a bunch of functions to compare floats. But I don't know which would be correct here. Nice. We can check for that. Can't you compute magnitude 2 and compare absolute value to 1? You're right. We can do that. Magnitude square. That seems a good idea. Because the magnitude needs to be 1, right? That's the definition of a unit vector. That seems a good idea. So how do we compare it? Let's see, std.math. Let's see what's in math. Approximate equals absolute. Hey, that's what we want. Performs an approximate comparison of two floating point values, x and y, returns true if the absolute difference between them is less or equal than the specified tolerance. Boom, immediately found it. It's kind of weird place to put that check assert comment. Initializing the hit should check for that, not some random function for that hit. But the point is that we're passing here. But here we are passing an outward normal. Are you saying that this function is not really meant to be called from the outside and it's only meant to basically be used down here? If that's the case, yeah, this whole thing seems silly. This smells. If that is the case, then this smells of object-oriented brain rot. To be honest, In any case, let's approx EQ ABS. We can move it. Approx EQ ABS. Type F64 X1 Y outward normal. I think you might be right though that this is I just saw that the code that the book wanted me to do this, and it wasn't immediate. It's not yet immediately clear to me what is the expected use case of this function, like where you're supposed to put it. Um, and maybe it's obvious if you know exactly what you're doing. I'm not quite there yet, right? So it wasn't immediately obvious to me that this is something that we're just gonna call in here. If that is the case, then yeah, we're gonna take this out. We're gonna put it down here, and like inline these things. And yeah, are we gonna call set face normal at random on a hit? Maybe, maybe not. If we are, then fine. If we aren't, then if we are, then fine, because we're gonna pass this argument here, and we need to validate that this argument is good for us. But if that's not the case, if we're always passing what we're computing here, then yeah, fuck that. Approximate equal absolute, and then the tolerance. I don't know what is a good tolerance. I think c.math has a good tolerance for us, doesn't it? Log none. Let's see, float, exponent, beats, mantissa beats, fraction beats, exponent, true, mean, max. Eps, is that the epsilon? Returns the machine epsilon of floating point of type t. There we go. That's our delta. Float eps. I think. I don't know. We're making this go through a square operation. Whatever. Oh yeah, you're right. 1 and 1. Thank you. Okay. So we're checking for this, and then we're doing front face, as in h dot front face is vec dot r dot direction. Oh wait, this also takes in array. Oh. Okay. And then h dot normal equals if front face, then outward normal. You know, we can even do this. We can do int from bool front. No, okay, it gets too clever. Never mind. Let's not do that. Front face, then outward normal, else minus outward normal. And then we delete this. Built in. There we go. Okay. So where do we use this? And then we add the surface side determination to the class. Yeah, it just calls this fucking function. Missing assert. Oh yeah, you're right. We need to assert this. So why are we even doing this? And then instead of doing this, oh, it's showing us the lines that changed, but copy sign. Yeah, I think this is fine. Okay, so copy sign. I would hope that LLVM understands this pattern and knows how to optimize it. I mean, it's so simple. Please, LLVM son, get this right. Okay, Okay, so we have P and N here. So we have T and P. So we're changing how we do N. Now we are doing this. We're not saving it inside. We're saving it. What is the point? Yeah, make it an init function. Yeah, I think you're right. That's a good point. This whole, I mean, I understand that this is not like a software engineering book that's teaching you how to do software engineering well, but that's what we saw just now. It's definitely a choice. That's for sure. That is for sure. That is indeed for sure. And then we do this, I guess. Okay, let's see how if I can get this right and not fuck it up. So this is gonna be our normal. Then there's gonna be the front face. Then we have to set T and P. T is root. So I guess we can call it T in this case, and it's gonna be a F64. But you know what? No, let's call it root. Actually, no. Why is it even called root in here? Find the nearest root that lies in the acceptable range. Oh, it's called root because it's the root of the, like, it's the solution to the equation. God damn it. Okay, so no, we call it T. So this can go here now. And this is T. This goes away. Okay, that seems right. I hope I didn't mess it up too much. We have our assert, we have our init. Does pretty much the same thing as before. With the only main difference that we flip outward normal based on the front face condition, which, oh no, we moved down here and now that is a problem. So we need to make this a, there we go. And this is a hit. And we don't take this in anymore. Okay, we're getting there, right? And then down here we do return dot init, pass in root, ray, and oh shit, we lost the outward normal. We lost the outward normal, which is this. Okay, let's see. Rack.p. Oh shit, the outward normal needs us to compute stuff. It needs p. Right, sorry. I kind of messed this up. Const p equals this. So I guess we don't do this. You just give me T and Ray, and we compute this inside. So outward normal is gonna be P minus center. We're gonna need a center, like 3, and a radius, F64. This goes here. Now hit only works. Hit dot. Wait. Now it dot what? Dot init. Oh, hit dot init only works for spheres, not all shapes. Oh, you're right. That is a good point indeed. Yeah. Good point. Good point. Okay, so this means that we need to take some stuff out. So const p equals this p minus center radius. So we pass in the root, which is the t, the ray, and then we also pass in the collision point, of course, and the outward normal. That seems fine, right? So we take in p as a vec3. Here we do p. Okay, this should be it. Did we do it? Actually, no. T is root. And here center is s.center and s.radius. Okay, I think we should be it. We should be there now. Sorry. Thank you, by the way, for catching this. That's a good point. Init needs to not be tied to a sphere. And this list of arguments makes sense. You know what? Let's add some comments to them, just to not forget. What is it? Length of the ray. Yeah, it's distance at which the collision happens. Oh, you know what? Whatever. So far, we know what they are. Fine. Okay, let's continue. A list of hittable objects. We have a generic object called hittable that the ray can intersect with. We now add a class that stores a list of hittables. Yeah, no, we're not doing any of these. Goodbye. Here's my hittable list. Look at how it's going to be. I'm going to go in main. And in main, we don't have this anymore. We're going to figure out what to do with ray color, but here's how it's going to work for us. We can have we can have in here something like this: const objects equals, and then we put them in here. That's it. That's all the code we need. What's next? Shared pointer. So they said that they were only using basic C++ stuff, almost FC, and now we're getting a lecture on shared pointers. Yeah, I don't give a fuck about this. Let's skip this stuff. Sure, PTR is included in the memory header. Yeah, good to know. Goodbye. Common constants and utility functions. We need some math constants that we conveniently define in their own header file. For now, we only need infinity. We have that. But we will also throw our own definition of pi in here. We have that, which we will need later. We also throw common useful constants for future utility in here. This new header, rtweekend.h, will be our general main header file. Yeah, like fuck that. We have infinity, we have pi, degrees to radians. I think we have in SED math this stuff, so we should be fine. And yeah, the rest of the stuff, that's fine. Oh, and now we're going down on a adventure refactoring all the header stuff. Okay, sure. There we go. Now ray color is different. Okay, so these are changes that we want to have. You need to copy hit function to hit all objects. I don't understand what you mean for now. So we need to fix ray color because we don't have its sphere anymore. So how does it work? If world.hit. Okay, wait a second. What happened here? So he made a hittable list, I guess. Oh, and it has hit. Oh, I see. So, okay, now I get it. So this is what I need to implement, like hit everything. Hit everything. How does it work? Ray, tmin, tmax. Same signature. But then it calls hit for everything in there. And then it finds the closest. It keeps track of the closest. And then returns if something was hit. And so it throws away all the hit objects. No, it doesn't, because hit record. Wait a second. What is going on here? Oh, yeah. Or hit record is the type, right? That they have types on the left. So okay, it saves inside of temp rec. But then there's rec in here. And then we keep assigning to rec temp rec. Okay. Sounds good. So where do we put this? This is like hit everything. I think it can be a function inside objects. So I'm going to copy this so that we don't need to wonder how it's implemented. I think I'm going to put this in objects.zig, I guess. Or should we put it in main? I think maybe this belongs to main. Because it happens to have the same signature. But it does, like this, by the way, it's another interesting thing about object-oriented brain rot. It has the same signature, but also because we're making a hittable list also hittable, but it's doing something completely different inside. Why do you feel the need to homogenize this stuff? What even is the point other than creating confusion? Like, I get that you might have a practical reason to have your individual objects, like your individual shapes, all be hittable. Fine. Why is a list of them also necessarily? Why does it have to be hittable in on itself? So let's not do this. Let's go back to main and let's implement this down here. Let's call it hit everything, I guess. Returns an optional hit. Sure. So we pass in, I guess, objects. We say then ray, then tmean, ray tmean. And that's it. Then in line 4, for each object, we call hit. And we pass down ray tmean, ray tmax. Then we maybe obtain an H, maybe not. So there's hit anything, which I think it's interesting and useless, but in any case. Although, you know what? Maybe I'm wrong. We'll see. So we hit something. I guess we have to save this hit somewhere, right? So we need to have a hit in here. Okay. And this needs to be optional. Then we assign to it. Then we save closest so far. Oh, we keep changing. Okay, one argument. So bar closest so far equals ray tmax. Closest so far. So far equals hit.t. And then we return hit. And that's it. I believe this is pretty much it. Maybe we should import hit, as a type from objects. Okay. Oh, but now we have a collision in the name it says objects. You are overwriting the result hit on every object now. Yes, I believe I am. Let me think. That's also what's happening here. So we pass temporec every single time. We read from it, and then we unconditionally assign it to the outer thing. Oh, you're right. It's an optional. Yeah, that's a good point. I didn't do this. So if hit, that is a good point. What do they do? Oh, they do the assignment unconditionally. Even no. Oh, right. Only if it succeeds, they do this stuff. Oh, thank you. Yeah. Yeah. Which I guess we can do this. There we go. Okay. Some new C++ features. No, please, dude. I have the enough of C++ features. Wait. I mean, we're missing a world. Or else continue. You're right. We don't want to assign. Oh, good point. Good catch. Yeah, we don't want to assign it unconditionally. Yeah. Which then, to be honest, we can do this then. We can assert that hit is accessible because otherwise we would have continued. Yeah. Okay. So anything else like about the world? Is there anything bunch of useless OP stuff? Look at how much garbage, man. Okay. The hittable list class code uses some C++ features that may trip you up if you're not normally a C++ programmer. Vector, shared pointer, make sure. Okay, please, save me from this stuff. Common constant. Wait, did we do this already? Okay. You need to pass. You still overwrite hit unconditionally. No. Wait, or maybe this was true earlier, but with or else continue, it does not happen. So with this construct, what's happening is that we take this value, and if we can unwrap it, if it's not null, then we assign it. If it's null, then we continue. So we don't do the assignment. Yeah. And I am passing closest so far, so we're good. Okay, perfect. So we need to do this, right? Ray color if world.hit return 0.5, and then here we're making the world. And so when we call ray color, we give it the world. Okay. So let's make the world first. Call it world. Fine. Make shared sphere. What? Objects. Oh, you know what? Let's also get those. What is going on? I got into Colimac for some reason. um. And so what do we do? 0, 0, minus 1, 0.5, minus 100.5, minus 1, 100. Okay. And then when we call ray color, we pass in the world. So ray color takes in the world. Any type for now. And this is where we do the last modification. Let's see what that looks like in Zig. So, well, this looks already good. If world, not world or hit, but hit everything. If hit everything, world are 0, infinity. This is std.math. I think it's just inf. Oh, inf of f64. And then rec we don't do. Hit. Return. Hit dot normal plus there we go. Then the if t, so this is not done then. And then uniter a, okay. Okay, so let's see. What do we get? Mixed scalar and vector operands. Vector and f64, right, objects. Line 97. Wait, what? Main does line 97, sorry. Objects line 60. We need to splat this guy. Then what's the next problem? Content control flow outside of runtime block. Oh, interesting. Let's see. So this is on in line 4. So we are getting punished a little bit by our use of comtime metaprogramming. Yeah, you can't do so. You can't continue. You can't do continue in an inline 4 if the condition that causes you to do continue or not is not also comtime. So that is indeed annoying. And I guess we need to change this basically. we need to switch it back to what it was before. So if h, then we do this stuff. Remove Raytracing and Tmax from params. What? Why? It should be hit anything. Why remove T-Remin, Ray-Tmin, Ray-Tmax from params? Why? We have them here. We use Tmin here. We use Tmax here. I guess you're saying because they were only passed because it was a virtual function. Oh, you're right. Jesus, that is so dumb, isn't it? Because you're saying that this always starts from std.math.inf f64, and this always starts from and this is always 0. That is yet another reason why it's kind of weird to try and make that be a hit, huh? Okay, so hit everything, go to references. Here we're using it, so we don't need to pass these constants, which is fair. Okay, let's see what else is there. Extracted type F64 found a function. Oh, wait, float EPS is a function. Oh, that makes sense. You need to pass the type of float. That's fine. That is fair. Let's see, mixed scalar and vector operands. Vector and right. Okay, main 79. This is actually vec.1. Mixed scalar. Oh. Splat. Yo, we got a runtime. We triggered the surgeon. We triggered the assertion. Ooh. So let's see what happened. Let's see if it actually asks float apps at. What's float apps at? Returns the local epsilon of floating point time t. Maybe apps is too small. Yeah, that could be it. But wait, why at? No, we still hit. Yeah. But we still hit, and we're supposed to be near 1. Let's make this 2. I don't know. Bigger epsilon. Let's see what this epsilon is. What is the epsilon, man? I guess we can play into the epsilon once. Oh, but well, we're gonna print it a bunch of times, so I guess that's fine. So 1, 2, 3, 1, 2. Oh, this is 4. Hmm. Here's what we can do. Let's do something like this, 0.001. Is this what we're supposed to see? I don't know. Let's see. Well, it is. Let's see. This yields a picture that is really just a visualization of where the spheres are located. Oh, right, because the bottom one is a giant sphere down below, right? This is, let's see, are located along with their surface normal. This is often a great way to view any flaws or specific characteristics of a geometric model, resulting render of normal's colored sphere with ground. Let's go. We got our ground. An interval class. No, bro. Enough with these fucking classes, man. Please. Before we continue, we'll implement an interval class to manage real valued intervals with a minimum and a maximum. We'll end up using this class quite often as we proceed. Let's see. An interval class to manage real valued intervals with a minimum and a maximum. So I think maybe this is a good place where to stop. By the way, for people who have done this already, how far along are we? Are we halfway done? What? No, it's almost 11 p.m., man. I've been streaming for almost 9 hours. It's been fun, but I think this might be not a bad place to stop. We reached another checkpoint. We succeeded at everything. There's more object-oriented programming insanity. Raytracing is a never-ending rabbit hole. Okay, yeah, no, I get it. I know that there's also the third book that is about spending your entire life trying to understand ray tracing, but so far in this book, I mean, I see that we are like 1/3 maybe of the way. No, we're a bit above 1/3 with what? Yeah, more or less 1/3 of the way. Yeah, I can push the GitHub. Yeah, of course. I would say this is not bad as a starting point. We've been streaming for... Okay, so this specific thing we've been doing for 4 hours and a half. So I would say this is a good place where to stop for now. So git status, cd source. I think we have a math file they want to remove. Everything else should be fine. Yeah. Git ignore. I'm gonna add emg.ppm. Actually, probably, you know what? Anything.ppm we might want to ignore. That's not a good idea. More or less halfway through. Okay, that seems good then. I think it's a reasonable point where to stop. By the way, I'm gonna do the second half tomorrow. It's ray tracing in a weekend. We're doing it in a weekend, like this weekend. So today the goal was to do, I guess, more or less half, and then do more or less half tomorrow. So day one, is there a way to say I guess 6.8? Day one, up to chapter 6.8 excluded. And we can push. There we go. So thank you all. I hope you had fun. I'm gonna stop the recording. So I don't know, say goodbye to YouTube, and yeah, we're gonna continue tomorrow with the second half. Yeah, that's it pretty much. So I'm gonna stop the recording now. Bye, YouTube.